Bienvenidos. Es un gran honor tenerlos a todos aquí. Gracias por aceptar nuestra invitación. Entonces, vamos a empezar. So, welcome everybody. So, this week we are celebrating Uniandes at the International Year of Quantum Science and Technology. Today, we are going to have a really exciting agenda, which is the following. First, we will have a few welcoming remarks by our Vice President of Academic Affairs, Professor Silvia Caro. Welcoming remarks by Professor Daniel Cadena, Dean of the Faculty of Sciences. And then we'll have the public talk by Professor Eric Cornell. And then we'll have a public talk by, we'll have a coffee break, but after there we'll have a public talk by Professor Ana Maria Rey, followed by a panel conversation. So welcome everybody again, and let's start with this exciting agenda.
Thank you, Jenny. Good morning, everyone. It is a pleasure to welcome you to today's event, which is part of Uniandes Week in the International Year of Quantum Science and Technologies. Professor Jimena Hurtado, our Vice President for Research and Creation, could not be here, but she sends her regards. Although this week's program includes many interesting events, the School of Sciences, led by the Department of Physics, has organized several activities throughout the year to bring us closer to topics that, while complex for many of us, are and will increasingly become part of our daily lives. Among these activities, I would like to highlight the exhibition, Exploring Quantum, a Legacy for Science and Technology, which was developed in collaboration with our library, and that seeks precisely that, to help us understand what quantum science means and why it is and will continue to be so relevant for the future. We are very grateful to all the faculty members, Alejandra, Jenny, Majerlin, Andres, Professor Bernardo, and many others, who keep the conversation about fundamental science alive within and beyond the university. I would also like to highlight that this event takes place within the framework of what we have called ERA 2048, which is a strategy through which our university builds upon the solid foundations of its history to imagine possible futures that will allow us to remain relevant and a reference in education and research for the country and the region. The year 2048 is very relevant as it is when we will celebrate our 100th anniversary. By the way, we are celebrating the university's 77th anniversary today. So please, if you have the time, pass by the different places in the university at noon. The central theme of ERA 2048 during this year is precisely research, creation, and innovation. A special recognition goes to the philanthropic program, Thinkers of the World, whose support has made it possible for us to host outstanding international researchers on our campus, including today's visitors. This kind of collaboration shows us how philanthropy strengthens education, research, and creative work, and allows us to participate actively in critical global dialogues. Today, we are very happy to welcome Dr. Eric Cornell, Dr. Ana Maria Rey. She is a graduate here from physics, from the physics department, Dr. James Thompson and Dr. Jun Yi, all of them from the Joint Institute of the University of Colorado Boulder and the National Institute of Standards and Technology, and world-recognized experts in areas related with quantum science and applications. Having them, having you here today is a true privilege for our university. Allow me to make a confession you may already anticipate. I don't know quantum physics. However, physics and especially quantum mechanics have always been part of my life. We were talking about it, but both my parents are physicists. I remember going with my mother as a little girl to the university's computer center to deliver punch cards to run a program for her graduate thesis. Later, seeing her write her book, Introduction to the Formalism of Non-Relativistic Quantum Mechanics, I also remember her talking about quantum algebras, writing hundreds of equations late into the night and discussing with my father the work of the students she supervised. Even though I never understood much or anything really, what was clear to me was the passion, discipline, and rigor with which she approached all these activities. That taught me two important lessons. First, to be diligent and responsible in my own education, but above all, to appreciate science, mathematics, and fundamental research. This is something that has stayed with me and continues to deeply shape the way I approach research. History has shown us that many of the technologies we use daily were born from ideas that once seemed purely theoretical. You may know the story of Charles Towns, the inventor of the laser, who used to say that his creation was a solution looking for a problem, since at the time, its potential applications were not clear. Today, that solution is an essential tool in communications, medicine, industry, and many other fields. This is why this week reminds us that curiosity, imagination, persistence, and patience are the essence of knowledge, and that such knowledge over time can transform our lives in ways we cannot yet imagine. So let us take the opportunity offered by today's event to learn and to be inspired. Thank you very much.
Morning. I won the Nobel Prize in 2001 for making the world's coldest stuff. Obviously, that wasn't me. That's how Professor Eric Cornell described his achievement, with the kind of simplicity that hides the depth of what is an extraordinary discovery. So Silvia said she doesn't know physics, but I'm a biologist. I know even less physics. But last night I did my homework and tried to learn a little bit about Dr. Cornell's work. I learned that about 30 years ago, in a lab in Boulder, Colorado, he and his colleagues cooled atoms of rubidium to unimaginably low temperatures, colder than anywhere else in the universe. At that point, I understand that the atoms stopped behaving as individuals and began to act in unison, as if they were only one. So as I understood it, that was the first Bose-Einstein condensate, which had been born, though it had been predicted many years ago. This, you could say, it was a new state of matter, or a new way of looking at nature. And also, I would add, it's a powerful reminder that without fundamental science, without curiosity-driven research that pushes the frontiers of knowledge, there can be no true applied science, no innovations that change the way we live. So today is a real privilege to welcome here at Uniandes the scientists who made this discovery possible, as the world celebrates the International Year of Quantum Science and Technology declared by UNESCO to recognize the significance of this field and its impact on society. So just a year ago, in this very building, we celebrated the arrival of the first quantum computer in Colombia. That moment marked the beginning of a new era for physics in our country and reflected this university's commitment to pushing the frontiers of knowledge and innovation. Our Department of Physics has a long tradition of research and teaching in quantum science, and in recent years, it has deepened that legacy by integrating new generations of researchers and expanding opportunities for learning. So throughout this year, as Silvia said, our School of Science has been especially active, not only in research, but also in public engagement and in shaping science policy surrounding quantum science. So we took part in the National Commission on Quantum Science and Technology at the Ministry of Science, Technology and Innovation, contributing to the design of a public call that promotes research in this area alongside artificial intelligence. We also made important progress in education. This semester, Uniandes offered for the first time an introductory course in quantum computing, which was created jointly by the Departments of Physics and Mathematics, and which has received extraordinary enthusiasm from students across disciplines. So this has been a fun year, and this week has been without a doubt a fascinating week of celebrations. So I want to thank Professor Cornell for being here with us, and also Ana Maria Rey, Junier, and James Thompson, three remarkable scientists whose lectures and conversations with our community have been inspiring and have left a truly lasting impression. I also want to warmly thank our Department of Physics for its dedication, in particular our three women physicists, Alejandra, Jenny, and Majerlin, for their dedication, the university library system for the exhibition that I invite you all to visit if you haven't seen. It's open until December 1st, I understand. And also to the Pensadores del Mundo World Thinkers Program of Uniandes, which made this visit possible. So thank you all for joining us this morning, and may this gathering and the celebration of this week inspire us to keep exploring the unknown, to connect science with society, and to continue building from Colombia, but connected with the world, a future shaped by knowledge, curiosity, and collaboration. So Professor Cornell, I think, needs no further introduction, but please join me in welcoming him to our university. Thank you very much.
No. How about that? Better? Okay. This is pretty good. Maybe I'll stay here. Maybe let's try about over here. Okay. I'm going to be talking to you today about using tools in the laboratory, precision measurement tools, to understand something much larger, basically something about the history of the universe. So I'm going to start with the very beginning of the universe, which was about 14 billion years ago, reckoned from this exact moment at Uniandes. There was a Big Bang. And then just immediately after the Big Bang, the universe was, as they say, in a hot, dense state. There were many, many, many particles. In fact, in the entire universe, back then, in these first microseconds of the universe, there were many more particles in the universe than there are now. And they came in various flavors. There were electrons and protons and neutrons and anti-electrons, anti-protons, anti-neutrons. It turns out in physics, for every particle, every kind of particle, there's an antiparticle. And exactly just after the Big Bang, it was extremely uniform and balanced. There was almost exactly the same number of electrons as there were anti-electrons, protons as antiprotons, and so on. And they swarmed around and bounced off each other. Then the universe began to expand. And as we've learned, for instance, in our high school chemistry class, if you take a gas like the universe and you expand it, it gets cooler. So let's see if we can do this with PowerPoint. You see how it goes from sort of red to sort of blue? Oops, that tells you it's getting cooler, yeah? And what happens then is something very romantic, actually. Every particle finds its true love. Every electron finds an anti-electron, a proton finds an antiproton, and they bind together. All around the universe, there are little miniature weddings like this. But unfortunately, these weddings were short. When the proton and the antiproton bind together, shortly thereafter, they annihilate each other, leaving nothing but light, a flash of light, and other than that, the particles are nothing but a memory and a flash of light. And this happened again and again and again. And all around the universe, most of the particles, most of the electrons found the anti-electrons, protons found antiprotons, and an enormous fraction of the universe basically disappeared and turned into light. Basically, it happened to everybody, except for, oh, wait a minute, oh, look over there. There's a neutron. This is sad. This neutron could not find an antineutron. This proton could not find an antiproton, and so on, this electron. It turned out that for every 1 billion electrons, anti-electrons, there were more or less 1,000,000,001 electrons. So there was 1 part per billion of material in the universe that did not annihilate. And so basically, we can ask ourselves, like, who are these lonely losers? You know, they can't find anybody. And of course, the answer is they're you and me. Sometimes I think to myself, this explains a lot, you know? But I must say, it's actually wonderful, right? Because if there hadn't been this slight imbalance between matter and antimatter, the universe would be a very boring place. You know, there would be nothing left but light. No hydrogen, no stars, no planets, no people, no Uniandes. You know, it would have been very, very boring. So this is wonderful. And it's a strange thing because there had been something approaching perfection in the universe, a perfection in the balance of electrons and anti-electrons, protons and antiprotons. And this is actually a flaw, a mistake, a tiny, we sometimes say in physics, a tiny asymmetry, a lack of sort of perfect symmetry of reflection that occurred and which had immense consequences. And so this exact matching up was not perfect, and humankind, all of us, was born of this original imperfection. So it's a matter of at least conceptual, enormous importance to us. Like, why did this happen? Why, when things were so perfect, why were they a tiny bit imperfect? And it's a difficult question to answer these days because it happened 13.7 billion years ago, and it's not so easy to understand things from that. We can't, despite what you may see in the movies, we can't go into a time machine and step back 13.7 billion years ago. There were no written records, no internet. You know, there's nothing we could look back. So it's a little bit like trying to find out about the dinosaurs. You know, even in the time of the dinosaurs, much more recent than the beginning of the universe, still we can't go up and read the history of the dinosaurs, at least as they would have written it. So there are sort of 3 approaches. I think of it as a 3-legged stool, a chair with 3 legs on it, that we can use to learn about the early universe and at the same time to learn about particles in today's universe. And one leg of this 3-legged chair is telescopes. There are many big telescopes. This is a conceptual telescope which is going to be in the southern hemisphere. It's not yet constructed. Gravity wave detectors, you may have heard of these. These are also a kind of telescope. Neutrino detectors, we don't think of them these ways, but neutrino detectors are also telescopes. They look at particles coming to us from far away. And these are also a way of looking backward in time. Because if we look up into the sky in a telescope and we see something which is coming from 10 million light years away, we are not seeing that galaxy as it is today. We are seeing that galaxy as it was 10 million years ago. If we look further and further back at things which are farther and farther away, we are looking further back in time. And the furthest thing, okay, this might be slightly outdated, but when I made this slide, the thing that we can see in the sky which is the farthest away is a galaxy 13.3 billion light years away. And when we see the galaxy, we see the universe as it was when the universe was only 4% as old as it is today. The universe was just a baby then. Not really a baby. The universe was, okay, in English we say a toddler, a little child who can barely walk, but not a baby. And unfortunately, by the time of this, the universe was, okay, 0.4 billion years old. These questions of the matter and the antimatter were already, at that time, ancient history. They had been settled. So we cannot look far enough back in time with these telescopes. So what else can we do? The other thing we can do is we can try to recreate in our laboratory a sort of miniature version of the Big Bang, something as hot and as dense as the Big Bang. And we can do that by smashing particles together. The Large Hadron Collider, which is in Switzerland and in France, In fact, the particles go around and they have to undergo frontier formalities. Every time they cross this dotted line, they have to show their passport, and then again and again and again as they go around and around. This is the largest scientific instrument ever constructed by humankind. And it was designed largely to answer this question. This is one of the sort of design questions, because they take protons, they smash them together, and for a fraction of a second, the universe was much as the universe was long ago. Unfortunately, the current consensus is that the collisions, if you like, are not sufficiently violent, if you like, to answer this question. So there is, happily, there is a third idea, a third leg of the chair, which is, I would call it looking for fossils. Here we can learn about the dinosaurs by looking at their bones. We want to look for the ancient bones of the early universe, the fossils of the early universe. And we look for them because the thing that matters most to us as people about the early universe is the fact that the universe was not perfectly asymmetric. We look to see fossils, call them distant echoes of this asymmetry today. Here's an example of a beautiful symmetry. My understanding is this does not happen so often here in Bogota, but in my city, falling from the sky at least multiple times per year are these beautiful pieces of ice, which have formed these lovely crystals. But this is actually a much more complicated piece of symmetry than the symmetry I'm thinking about. In physics, there are three of the most important symmetries, which are very basic. One is exactly what I was talking about. Electrons act just exactly like electrons, protons like antiprotons. We know that that symmetry is not perfect, or at least it was not perfect at the beginning of the universe. We also know that most particles, if you look in the mirror, they look exactly the same. You get up in the morning, you look in the mirror, and you maybe aren't certain whether you're looking at a mirror or looking at a photograph of yourself. You look pretty much the same. That's true for many of us. It's not actually true for me. I look in the mirror and I see someone who's missing a right arm. I don't know if it is a coincidence. We would have to consult with Freud, Sigmund Freud or something like that. Is it important that I started to study this fundamental asymmetry the exact year I became a fundamentally asymmetric person? Who knows? Okay, but we find out that yes, when particles look at themselves in the mirror, they look very similar, but actually not exactly the same. And then this is a slightly more subtle one, which is particles look the same if you run the mirror backward. If an electron and a proton collide with each other and you take a movie of this, and you show someone the movie running backwards of an electron and proton colliding this way, they can't tell whether the movie is running forward or backwards. So these are the three basic symmetries, and this is something I have to sort of skip because it gets very theoretical, maybe too theoretical for me to understand. But there are theoretical physicists who say, if only we could find examples of this kind of asymmetry, the kind of asymmetry which can result, for instance, in these particles not looking the same in the mirror, for instance. If we could find these things today, it would help us better understand the very important initial asymmetry which happened now 14 billion years ago. The key hope, and in some sense this is just a prejudice or something like a sense, is that we think that the rules of physics themselves don't change. So if we find explanations today, these apply backwards as well. Okay. So what would be an example of an asymmetry? Here's a Mr. Electron. You can tell the electron is a very friendly and easy to understand particle because we can write about him in Comic Sans font. Okay. The electron, as we all know, has a charge of -1 in fundamental units. It has a mass. It spins. Because it's a charge and it's spinning, it has a magnetic field. We say a magnetic moment, meaning it's got a north pole, a magnetic north pole, and a magnetic south pole. And for a long time, we thought this was roughly all there was to know. But then we can ask the question, are the north pole and the south pole of the electron exactly the same? Which is the same question as, do the electrons look the same if we look in the mirror? And as far as we know, maybe yes. It doesn't have to be. Here on the Earth, the North Pole and the South Pole are extremely different. In the North Pole, there is sea ice. In the South Pole, there are mountains. In the North Pole, there are polar bears. In the South Pole, there are penguins. If ever you happen to see penguins and polar bears in the same place at the same time, you know where you are. You are in the zoo, right? And there's no place, no other place. So it's possible then that the north pole of the electron is a little more positive and the south pole is a little more negative. We can think of the negative part adding up with this, the main negative part of the electron, and the positive part canceling a little bit of the negative part. And so this thing of having a positive and negative part is called an electric dipole moment. And it's a reflection of what could be an important asymmetry of the electron. And we can think of it as the center of the charge of the electron not being in exactly the same place as the center of mass. Now, I should tell you that anytime anyone has ever tried to measure this offset, this difference, they find a number consistent with 0. And even 10 years ago, it was already measured very, very well. They knew that if this offset existed, it was less than 10 to the minus 27 centimeters. I would like, it sounds like, hopefully it sounds like a small number to you with a 1 with 27 zeros before it, But even by the standards of electrons, which are very small, it's a small number. The size of an electron is roughly 10 to the minus 13 centimeters in some units. And the asymmetry, if it exists, is less than this, which tells you that, fractionally speaking, the offset between the center of charge and mass is 14 orders of magnitude smaller than the size. It's sort of comparable to, if you had the same sort of thing scaled up to the size of the Earth, you'd have like just a few extra atoms on the North Pole and not on the South Pole, something very tiny. So one more time, why again do we care so much about these things? And in physics, and this is a little difficult to explain, particles are never completely pure particles. They always, in the jargon of physics, we say particles are always dressed by other particles. So the electron, as we actually measure it in the laboratory, is really equal to electron plus tiny little bits of all the other particles, sort of floating in a little cloud around each electron. And so we may find around the electron a tiny bit of some other particle, as yet unobserved particle, which can represent, can be causing this asymmetry. So perhaps it looks like this. It doesn't look like this, but perhaps it does. In any case, this is a unicorn. We could call it the U particle, as yet unobserved. But if some particle like this existed and a tiny fraction of it floated around the electron, it could account for two different important things. It could account for why the electron is asymmetric, and it could also account for why the early universe had this very, very important asymmetry. It might. This is a hypothesis, and in order for us to come to believe this hypothesis more, we have to see if the electron indeed has an electric dipole moment. And so my group has been working on this now for some 20 years, and I work very closely with my colleague, Professor Jun Yi, who we see in the front row. We've been working on this project for a long time, and it's been a lot of fun, because Jun is himself a lot of fun. Okay, how do we measure it? Well, who is it to measure it? Here's a picture of the group. We're on a mountain. Just outside Uniandes, there are two mountains, and just outside University of Colorado, there's also a mountain, and it's possible to climb to the top of it. And we are on the mountain just outside of, as you go higher, it gets colder. I don't know why exactly. It's a physics thing probably, but you can see it's quite cold there. Yeah, anyway, these are the students who are working on the project. And we're trying to measure something very, very small. So there's an important rule in experimental physics. If you want to measure something very carefully, change the thing that you want to measure into a frequency and measure that. Because frequency, or equivalently time, is the quantity that we measure best in physics. If you see a measurement that has 7 or 8 digits of precision, it was almost certainly measured in this way. Somehow they managed to convert the interesting quantity into a frequency and measure the frequency. Here's an example. So here's a grandfather clock. It's roughly as tall as I am. It has a pendulum in the middle of it, and the pendulum swings back and forth. This is advanced PowerPoint skills. Look at the pendulum swinging back and forth. Why does it pull back and forth? Well, when the electron moves to one side, sorry, the electron, you see where I'm going. When the pendulum moves to one side, it goes up a little bit, and gravity pulls it down, and then it pulls back, and then gravity pulls it down again. And so it actually turns out to be the case that if we measure, oops, okay. It turns out to be actually a very accurate way to measure gravity. If you measure the frequency of a pendulum swinging back and forth, you can measure the strength of gravity. And you'll find that if you go a little higher, gravity is a little weaker, a little slower, and so on. And if you were to change gravity by a tiny bit, you would measure a slightly different frequency. At GILA, thanks to the work of some of my colleagues who are here today, we can measure changes in the frequency of a clock as small as 1 part in 10 to the 18. So we measure frequencies really, really well. And in fact, this is a great way to measure gravity. But it doesn't have to be gravity. We could measure the strength of a magnet, for instance. So you know, a compass is a magnet which can swing, and it will tend to point towards the North Pole. If we take, so here we have a big magnetic field and a little magnetic field in between. If we turn it to one side, the South Pole is attracted and it swings back and forth. And if we measure the frequency at which it swings back and forth, tick, 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 we can measure the strength of the magnetic field, or in particular, the strength of the magnetic dipole moment. This is exactly the way that magnetic resonance imaging works. Inside us, we have water, and water has protons, and the protons are little tiny magnets, and when the magnets wobble back and forth, they emit some radio waves, and we can detect these radio waves and understand where the water is located inside of us. Okay. But we're not interested in the proton, we're not interested in magnets, we want to know about the electron electric dipole moment. So we can take an electron and we can put it between two magnets. We could also, in addition to the North Pole and the South Pole, we could add a little negative charge, a little positive charge, and if, we don't know, but if the electron has a little electric dipole moment, the frequency at which it swings back and forth will change a tiny bit. But we're very good at measuring these tiny changes. There's two problems with this. One is that if we apply an electric field which is too large, zap, you'll just get sparks, you know, and so you would like to apply a very large electric field because this dipole moment, as we call it, if it exists at all, it's very small. And the other is if you try to apply an electric field to an electron, it just flies away. That's what electrons do when you apply electric fields to them. So where in nature can we find a really strong electric field? Okay, so I last took a chemistry class when I was in high school, 45 years ago, more than 45 years ago. So my chemistry friends tells me this is not the way molecules really work. But in high school, what they told me is the way molecules really work is that some atoms are positive, like sodium, and some atoms are negative, like chlorine, and they stick together. Apparently that's not actually true, or at least that doesn't account for most of them, but it is the case that this is true for some molecules, and if you were to take an electron and put it right between sodium chloride or salt, it would experience an enormous electric field, a much larger electric field than we can create by ourselves in the laboratory. And so we in particular use a very heavy molecule, atom on one side, hafnium, sometimes thorium, and a very, very negative, even more negative than chlorine is fluorine. And this molecule is has an enormous electric field inside. And we use this molecule as a laboratory in which to study the electron. Okay, so if we want to compare these frequencies, what else do we need? We need to measure the frequency really well. Suppose you have two sources of frequency, in this case, two grandfather clocks, and they're ticking, tick, tick, tick. They're both ticking at more or less the same period. We want to know, is one going a little faster, is one a little slower? The first thing you might do is you could wait for a minute. You'll find that one clock ticks 60 times, the other clock ticks 60 times. Well, that's the same, right? Or we could wait for an hour and count the ticks for an hour, 3,600 times in both cases. But if we wait for a day, wow, finally we see, and takes a lot of patience to count 86,402 ticks, but we might find that one has one extra tick over a day. So if we want to compare the frequencies really well, you have to look at them a long time. Okay, it's a standard principle in physics. So we have to watch them for a long time. So we have to watch our electrons ticking for a long time, and so we keep them in a trap. This is not actually a trap for our molecules. This is a trap for rabbits. We instead use an ion trap. Conceptually, there are cylindrical pieces of metal. We charge them up and apply voltages to them, and the voltages push the ions around and confine them to a little ball in the center of the trap. Our trap actually looks like this. It's a little hard to see, but it's very pretty. It's coated with gold. So it's a little vulgar, perhaps, but we think it's pretty, and against the blue background, very nice. Uh-oh. Uh-huh. Mm-hmm. Mm-hmm. Okay. This is a little jumpy. Okay, so we trap them in there, and then we take the electrons and we tilt it to one side, and they swing back and forth. They go tick, 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 and we count them for as long as we possibly can. And we compare to see whether the electric field changes the frequency of the tick. In this case, you can see them. This is sort of measuring the thing going back and forth, ticking back and forth, up and down in this case. And you can see that, it looks like about a second across there, and 1 second it's ticked about 20 times, more or less. So it's a very slow ticking period, and it's slightly different depending on whether or not there might be an electric dipole moment. How do we listen to them tick? We use lasers. We can't actually go in and grab the electron and tilt it to the side. So if you come into our laboratory, it's a laboratory. What you mostly see are lasers. We have maybe 10 lasers in our laboratory whose purposes are to carefully align the molecule, adjust its vibration, its rotation, and then set the electron to ticking and then measure whether it's ticked or not. So in this room full of lasers, the experiment itself is way off in the corner there. There's the experiment. Everything else is lasers. The apparatus is actually quite complicated. The molecules we make are created by evaporating some hafnium, mixing them with some fluorine. They travel along, they come into the center of this ion trap, and we hit them with lasers to knock an electron off. The whole process is many, many steps. We use a computer to control all these different steps, to sequence all the different pulses of lasers and so on. And I won't walk you through all the different processes because it becomes a little technical, but at the end, we can sort of count these ticks. And we count the ticks 2 different ways. We do the experiment twice, once with the molecule lined up in one direction, and then once with the molecule lined up in the other direction. And that changes the sign of the electric field, which changes whether the electric field is making the electron tick a little faster or a little slower. And so we do what's called a differential measurement. We see small changes in the frequency. We spend most of our time, we would really, really like to see this frequency be different. But our experience has been, if you really, really want to see something, sometimes you see it, even if it's not there. Your wishes make it become true, But we know that that's not what we're about as scientists, and so we spend a lot of time trying to convince ourselves that we're seeing what we think we're seeing. So for instance, we put a lot of effort into making the electric fields and the magnetic fields in the center of our trap very spatially uniform, so they don't change everything. But we can move the ions around in the trap by charging up one of the electrodes a little higher, one a little lower. And as we move them around, we can measure the frequency. And you can see that as a function of the location of the ions along the x-axis, you can see the location of the ions in the radial direction of the trap. We move it a few millimeters. We measure some frequencies. We see the frequencies change also as a function of their location in the z direction. We think about what this means. We spend a lot of time thinking about the imperfections in the trap. And eventually we come to a point where we feel like, yes, we see these imperfections, but we can explain all these imperfections. We can account for all these imperfections. We can subtract them away and be left with what we believe is a true signal of the electric dipole moment. This takes us multiple years, actually. It's how we spend most of our time. The other thing we do, again, in an effort to keep ourselves from fooling ourselves, is we take data, as we say, blind. We basically collect the data and we tell the computer, computer, please lie to us. Every time we measure, we take a few measurements, the computer averages all those measurements together, and then it adds to the measurements a number, a random number. And it doesn't tell us what the number is. What this means is, we would love to see this difference. We would love to see the example of the electron having an electric dipole moment. It would be a very significant discovery in physics. And we would love to see it so much that what we might do is every time where we see a number different from 0, we say, oh, the experiment's working really well today. Let's write that number down. And every time we see a number which is equal to 0, we say, it's just not looking that good today. Let's throw that number out. We are not, okay, I would like to say that we are not dishonest people. We think we are just as honest as other physicists, and maybe more honest than some physicists. However, the psychological pressures are very strong, and we are only human. So we ask the computer to lie to us. We collect an enormous amount of data over the course of a year or two, and we don't get to see the average as it comes in. You know, we don't know what's going on. It's extremely stressful. So comes the day when what we can do is we can look at all the points, we subtract out the average. Here, the average of all our points, it's a histogram of all the different measurements. This represents several thousand measurements organized in a histogram. But we tell the computer, take away the mean and just plot it here. We can see that, yes, our results are a Gaussian distribution. We understand the statistics. We know how large our error bars are going to be when we finally see the answer, but we don't know the answer. Then, one day, we tell the computer, give it to us straight. We are ready for the truth. We've decided that we understand all the errors. We want the actual number. This was, I would say, one of the tensest moments in my scientific career. We've done this a couple times as we've done more experiments. We don't know what's going to happen. Over the course of every time someone has tried to measure the electric dipole moment, and people have been doing this for more than half a century, they measure a number consistent with 0, but the error bars have been getting smaller and smaller. So the axis there on the left is not the electric dipole moment, but the error bars on it. And it's been getting smaller and smaller. The measurements started to get much better when the experiments went from using atoms to using molecules. And for all these years, we've had, for maybe 10 years now, we've had, I don't know how many of you read comic books, but there are superheroes. And then there are the supervillains, yeah? So I would like to introduce to you Harvard and Yale. They're not the superheroes. They're our competition. Honestly, we know them all. When we meet at conferences, we drink beer together. But for the purposes of this professional situation, whenever I say Harvard or Yale, I would like you all to do as we would do in the movie, in the cinema house in the United States when the villain arrives. Harvard and Yale. Thank you. Yeah. So anyway, there was this measurement by Harvard and Yale. Yeah, that was very, very good. We came along and we made a measurement which was, this is Jilla. Yay! Here they come, the good guys. We made a measurement which was almost as good. And then we thought, well, we call it, you can see our measurements have the same error bars. Let's just call it a tie, shall we? No, we thought it was going to be a tie, but then Harvard and Yale made a much better measurement. And you see it's one tick down there, but this is a logarithmic scale. They announced one day that they had done a factor of 10 better, which was, call it a wake-up call. It created a lot of interest and excitement, and I won't say despair, but a lot of focused attention in our laboratory. But just a few years ago, we made a measurement, let's see if it shows, yeah, which was better by about a factor, they made a factor of 10. Okay, I see, I'll put this on the screen later. Sorry, this is all jumpy. Okay, so we made a measurement just a couple years ago, and we knew that the error bars were going to be better than their error bars by about a factor of 2 or more. What we didn't know is what the answer was going to be. So what we knew is that, you can see up there is the Harvard and Yale measurement, and you can see that the error bars are such that basically it's consistent with 0. If you're off by only one error bar, they would call that a 0 measurement. We knew that our error bars were going to be a factor of 2 smaller, but what we didn't know is what was our number going to be. It could have been all the way out there at 1, and we would have seen a non-zero electric dipole moment with a 5 sigma result, a spectacular result in the sun. Or we could have measured something all the way on the other side, which also would have been a 5 sigma result, but it would have been in very strong disagreement with the Harvard and Yale result. And we didn't want that because we didn't want to embarrass the Harvard and Yale people. Put it that way. But in fact, what happened? What happened is we measured this. So yes, the error bar was smaller by a factor of 2, even a little more, but consistent with 0. I don't really want to, in this popular level lecture, to try to connect with you what this tells us about particle physics, but what I can tell you is that it allows us to say that so far, 1, we haven't found an explanation for this early asymmetry of the universe, but maybe more immediately relevant is we can tell you that if there are certain classes of hypothesized new particles, exotic new particle physics that we now know are not true, because if they were true, this number would not be at 0. So let's see where we're at here in my slides. Oh, it was on the cover of Science magazine. You know, this is in the United States, if you are a rock and roller, you want to be on the cover of Rolling Stone magazine. Here physicists want to be on the cover of Science. Okay, so earlier on at the beginning, we thought, well, perhaps our hypothesis is that the electron is partly an electron and has a little admixture of the U particle in it, which could account for this asymmetry, but our measurements have killed the unicorn. But, yeah, so there's no there, but let's see, maybe. Oh, yeah, okay, so there may be some other possibilities. The particle physicists are infinitely ingenious. They're always coming up with possible new particles. I don't think it looks exactly like that, but again, I'm not a particle physicist. To see this effect, we need to do perhaps a factor of 10 better. So we're working on doing a factor of 10 better. And I won't talk to you a lot about it, but okay, there's our new measurement. We hope both the Harvard and Yale group and our group hope to have a measurement which is roughly factor of 5 or 10 better, which will allow us to see, in essence, further back in the universe or into more massive and more exotic new particles, and that's coming soon. So I think at this point, I will stop and I will thank you for your attention. Oh, I'll just show you this picture of they're building the new experiment there. These are the students building the new experiment, and there is one student, you can see we've already put the new experiment into the vacuum chamber and we're starting the experiment essentially now. So come back in a couple of years, I'll tell you.
So now we have time for a few questions. So maybe we'll have a couple of microphones. So if you want to raise your hand so a microphone can reach you. So any questions from the audience?
I am not scary. You can tell because I use Comic Sans font on my slides. That's how unscary I am.
Question there. And,
Hello.
Hi.
I just had a quick question about, in this whole process of measuring this quantity with your team, what do you think was the biggest setback or the biggest obstacle? Was it a financial barrier from the university? Did you have any setbacks with the personnel? What has been the biggest challenge in this whole process?
So many challenges. It's a very complicated, you mentioned the financial things. These are a challenge. It's a very complicated experiment. 9 lasers, extremely expensive. It's a large experiment by the standards of atomic physics, and it was difficult to find the money for it. We had to go, yes, to United States funding agencies, yes, to our own beloved National Institute of Standards and Technology, but also even to private foundations with our story and our hat in our hand. And eventually we were able to pull the money together, but it was not easy. There were sociological difficulties. To take all this data to make the error bars so small, we had to collect data for 600 hours. And a lot of that 600 hours was very boring. and some of it was very frustrating. You know, the experiment would keep breaking, and we were 3 or 4 students and a professor or 2 in the laboratory, and we'd work and work and work, and eventually, you know, people would just get grumpy, you know, unhappy, you know, nothing, just again, just sort of human things. So I felt like it was a matter like, could we get enough data before some sort of dramatic homicide took place or something? In the end, yes, everyone survived and we're all friends again, but this is difficult to sort of work under these stressful conditions. That was a problem. There were some very tiny errors that occurred that when we constructed the experiment, we did not anticipate. In retrospect, we built the experiment out of stainless steel, a kind of stainless steel which is non-magnetic. But in fact, a principal fact of non-magnetic steel is that it is not non-magnetic. And it really should be called less magnetic steel. And the residual magnetism in the steel was a problem. If I could do my life over again, we would have constructed it out of titanium. That would have cost another $50,000. You know, I'm not sure we had that. So these sort of things came up. We were able, in the end, to very carefully characterize the magnetic field and subtract out its effects. But this was not, there was a time when we were taking the data when it was not clear that was going to be successful, and all the data might have been essentially useless, which would have been really sad. So we had many obstacles, and somehow, partly by hard work, but also occasionally by luck, you know, things worked out okay.
Right, thank you.
I see there's a question here.
This is kind of a two-parter. So first off, you're referring to symmetries for elementary particles. You said one of them was looking in the mirror. Were you referring to chirality of the particles?
I was actually referring to parity and not chirality. Yeah.
Okay, great.
Yeah, just.
And the second one is, what was this wishful thinking in the moment? If you were to transport your head back into that moment where you didn't know the results yet, what was this wishful thinking that you think what was affecting the outcome of the results? What do you want it to be?
Oh, so I can tell you exactly what I want it to be. It's not everybody in the group wanted the same thing, because if you know, the nice thing about taking data blind is that you can be honest with yourself and with others about what you actually want. You know, it's bad for the psyche to suppress your desires all the time. You know, so what I want. So I had there was a student whose concern was, if we measure something which is dramatically different from 0, and then later it turns out to be wrong, that will be humiliating. I wanted a number to be dramatically different from 0. I say, we will risk the humiliation. You know, no risk, no gain, you know. So I really wanted the number to be out on the right side, consistent with the Acme number, but also distinctly inconsistent with 0. That was my heart's desire. And then, but so people, we had different ideas. But what the answer is the answer, you know, so. Here's a question. I see there's some questions down there.
Thank you for the talk, was excellent. So making these precise measurements, as you explained, it rules a lot of models, rules out a lot of models.
Yes,
of course.
Yes.
But then
good.
if it turns out to be really 0,
Yes.
yeah, so what are the alternatives are there to explain these kind of asymmetries there?
Well, first of all, I think there is no one who believes it's going to be 0. However, there are many people who believe it's going to be much smaller than what we can see. It's possible to construct models which give the electron-electric dipole number a very small value, and yet can still account for the asymmetry, early asymmetry. So I would say that particle physicists the theorists are infinitely inventive, and you give them a set of facts and they will construct theories around them. But as for me, I don't have that skill. And so I was not a successful theoretical physicist in my early days. And good with the soldering iron, the oscilloscope, I used to have very nicely coordinated hands. Now I have nicely coordinated hand, but still not a particularly good calculator. So
now that I still have the microphone, a second one. So now you seem to have gained some momentum in the precision of your measurement.
yes.
So, how much time do you foresee to get
Our next
one of
measurement?
the, yeah, exactly, one order of magnitude better or so?
Okay, so our immediate goal is between a factor of 3 and 5, give or take. And it's funny, we just finished a bunch of design work, and we went down to the instrument shop in the basement, and we were talking to the machinists, and we said, we want this to be this precision, and they said, they take the pencil from behind their ear, and they say, yes, we can do it. They will take at least 2 or 3 months. We'll have to install this improved device. Then we have to commission it. I think about 3 years. I think we'll have a factor of 3 in about 3 years. The next factor of 3, I will not lie to you, is going to be harder. And we have plans for that. But it helps to take a step before you plan your next step. And so I can tell you a little bit. We plan to have one thing, the biggest change we've made is we've moved from hafnium fluoride plus, hafnium being a very heavy metal, to thorium fluoride plus, thorium being a still more heavy metal. Probably we should have done the experiment originally with thorium, but right when we were first planning the experiment, there had recently been a tiny, tiny little accident at NIST where a tiny, tiny amount of radiation had escaped. And from a political point of view, at that particular moment in time, using a radioactive atom in my laboratory was not possible. Thorium is very not radioactive. I was talking to the safety officer, and I said, were you aware that it is not possible to consume, eating, enough thorium to die of radiation poisoning? And he said, that's ridiculous. I have a calculation here. I said, no, because even if you've eaten only 1% of that amount, you will die of heavy metal poisoning first. So I said, do you feel reassured? He was not reassured. I thought he would be very calm after that, but no, somehow he didn't find that a very relaxing thought. But so. Here's a question.
Thank you for the nice talk. I have a couple questions. So the
Please.
first one is this Harvard group using the same technique as you?
No, they use a very different technique. And actually, the slide is old. The various professors are wandering around. One of them is at Harvard. One of them is at Northwestern University, and one of them is now at Johns Hopkins University in Baltimore. But it's easier to say Harvard-Yale also, because also it sort of suggests that we are David and they are the Goliaths, Harvard-Yale. In order to compete with us, Harvard and Yale had to combine forces in order to, their experiment's really quite different. We have very long coherence times. Just use the technical term, our Ramsey pulses were 3 seconds long. So this is very, the quantum coherence continued for 3 seconds. So our line widths were only 100 millihertz or something. Their coherence time is 2 milliseconds. So their intrinsic line widths are 1,000 times larger than ours. So you might think, well, their line is 1,000 times larger. They won't be able to find the center very well. They overwhelm that by having an extremely high count rate. And so their statistical precision accumulates very rapidly. Whereas we have, they're using neutral molecules in a beam. They go through fast. The coherence times are short, but their count rate is high. We have ionic molecules in a trap because of space charge. We don't have very many ions. Our count rate is very slow, but our coherence time is long. It's amazing that we have, line widths which differ by a factor of 1,000, but an overall errors which differ only by a factor of 2. It tells you that their intrinsic signal to noise is basically 1,000,000 times higher than ours. So, and it's how strange that they should so precisely cancel. But
Yeah, I am asking because I'm very surprised, all the technical skills that you have to have in order to measure for 1 year and have the laser very stable and having all these ions. So it's amazing. And that reminds me of an experiment that somebody else is doing, G-2 maybe?
Yes, it's very similar.
So that made me think that if maybe looking at the resonance, like the G factor of the electron can also give information about what are you looking for?
100%. Yeah. It's interesting. The magnetic dipole moments and the electric dipole moments address very similar physics. They both have short-range effects, meaning short range in physics means very massive. Virtual particles that are very massive can affect both electric and magnetic dipole moments. Our raw precision, our sensitivity in the electric dipole moment experiments are higher than the sensitivities in the magnetic ones by quite a bit. However, we are sensitive only to physics which violates CP symmetries, where they are sensitive only to physics which does not violate CP symmetries. So we are in some sense, we are looking in different sectors of a hypothesized new physics. The groups of people who are sort of looking at magnetic dipole moment, G-2 is just magnetic dipole moment, and electric dipole moment, these are overlapping Venn diagrams. I mean, people with the same goals, oftentimes in traps, graduate students and postdocs diffuse between these experiments because the technologies are very similar. And, but yeah, also very promising approaches.
And you may have another question. So since you have this that you pretty sure that is close to zero now, the effect that you were looking for. So, and now you have this big machine. So what else are you looking to use it for?
Oh, yeah. I don't know. I'm really worried that it's a fairly specialized machine. And well, you can see it's 1.5 meters long, and I would love to be able to tell you that we will be able to do quantum information experiments in it and so on, but it's been under development, and so I've been thinking about this problem for 20 years. It's been under development for 20 years. June showed me how to do spectroscopy in a discharge with combs and everything like that. All of this work for 20 years was focused on a very particular idea, and we weren't building these things with the goal of having a general useful spectroscopy device, but with a very intense, for me unusually, because earlier I had been doing ultra-cold atoms, Bose-Einstein condensation, where there are many possible directions to go to. You make yourself some cold gases, all sorts of different things you can do. With this experiment, there's not many things you can do. I will say that instead of measuring the dipole moment of the electron, you can measure the dipole moment of the nucleus within the atom, which addresses very similar physics, except as they say, in the hadronic sector instead of the lepton sector. And those experiments are really quite similar. And so it's funny you should mention that, because I have had some discussions with people that when this experiment retires, roughly the same time I retire, there is a possibility that June and I will send the equipment to a facility where they have short-lived radioactive isotopes, which turn out to enhance the sensitivity of the hadronic effects. It's still a dipole moment experiment. It just happens to be in a very different part of particle physics. So it may yet have a second life.
Then maybe I have a...
Whoever's speaking. There you are, yes.
It's just maybe a question about the projects. Like, how do you pick and choose exactly where, like, what you're gonna do? Like, I feel like you need like a ton of foresight, right? You spend like 20 years and a ton of funding, and at the end of the day, I think it's measurements that are like very, very precise, and you have like fierce competition. So, like before starting like the project and things, and like, how do you decide like, okay, I'm gonna just focus on this, and then how do you know like when to stop, when to focus on other things, and like how much time do you like need to spend on it, right?
So if you look at a lot of successful experimental physicists, what they have in common is they're not very realistic. They tend to be tremendously over-optimistic. Nobody, certainly not me, would ever start an experiment that takes 20 years. That's ridiculous. By the time the experiment's done, it's not going to be relevant anymore. I have done 2 experiments that took 20 years, but none of them were supposed to take 20 years. They were supposed to take 4 or 5 years. And so this ability to be a little bit, obviously, you're constructing something very complicated. You're very much tied down to the real world. But it's helpful not to be too tied down to the real world, because if you're being realistic, probably the experiment is not going to work. Probably, you're going to, probably some other group is going to do it before you and render your work irrelevant. It's helpful to be, have your glasses with a rose tint installed in them. I'm going to get new glasses. Everything looks a little rosy to me. And so that helps. I hesitate to offer this advice because, in fact, it's also, one needs to be kind of hard-nosed, but not too hard-nosed. Yeah.
Yeah, thank you. Then maybe just a follow-up. I think it's also kind of hard because physics is very much so a collaborative effort, right? I think physics is built on everyone working together. But then again, in the real world, you go out and you get funding to actually get results and then get better results than other people, right? So in conferences and stuff, I feel it can be a bit weird. How do you go about discussing your findings and things? How do they manage that sort of stuff, right? How does information go between universities and stuff?
I'm not sure I completely understand the question, but it's 100% true that physics is immensely collaborative these days. And so this project was too large for one professor. I've mentioned Jun Yi, but we also work very closely with a number of theoretical professors who give us insights about molecular structure and molecular dynamics and things like that. And then the people who really do all the work are graduate students and postdocs. And one works with a big group, and one discovers that not everyone is motivated by the same things. People want different things. They're doing it for different reasons. And somehow that project all has to come together into a successful collaboration. And it's never easy. It helps if you start with people with goodwill and a sort of cheerful approach to life. Because if you're tending to be gloomy, experimental physics can make you more gloomy. But I don't know. The world of experimental physics has been done in a very collaborative way for decades, and somehow as a profession we've found a way to make it work. But I'm not sure if I'm answering your exact question.
Yeah, that's kind of about it. More so, it's also about collaborating with other universities, right?
Yeah.
I feel basically what you said in your presentation, right? It's a collaborative effort, but they're also the enemy, right?
Not really.
I know it's not really like that, but you do hope to get better results in them, right?
Yeah. I can't emphasize how much I personally like these 3 guys, the villains, in the movies, Dr. Doom or whatever arrives, and Spider-Man never has a beer with them afterwards, but we do, Although maybe if they did, they wouldn't fight so much. The movies would be less interesting. The competition is good, it's hard, and it can prompt creativity, and keep you from, sort of the sort of nervousness one feels about, FOMO, falling behind, things like that, can be the thing that sort of prompts you to have an interesting new idea. Sometimes a little bit of desperation is a good thing, and that can come from the sense of competitiveness. So if it's too strong, it can destroy people's morale and can actually be counterproductive, you know. The experiment we're currently using, we moved to thorium. We have a little piece of thorium inside the experiment. It's very difficult to get thorium. The piece of thorium that I got was given to me by the guy at Harvard. I mean, maybe I can put it that way, which tells you something, right?
Yeah, absolutely, yeah. Okay, thank you very much.
Time for one last question. Here on this side.
Hi, what would you think are the most important consequences of your discovery? Like, if the number turns out to be different from 0, what would you think some theory needs to be like changed or something like that?
Okay, so what I should emphasize is that if you're trying to validate an entire new model of particle physics, one number, no matter how precise it is only sort of measuring one dimension. You know, it's kind of like, say your particle is an animal and you measure the length of its leg or something like that. So the idea is that there are around the world other precision measurements. Eventually these measurements might inform the more traditional form of particle physics where you would construct an accelerator optimized to maybe see a particle. Now, if you kind of know how massive it is and how strongly interacting it is, you could construct an experiment more precisely aimed at that. So this one number isn't going to say, okay, here's the answer to all of future particle physics. But it's a piece of the puzzle. I am not myself a particle physics model builder, so I can tell you that with a given strength of interactions between an electron and a hypothesized new fermion or some new boson, I can tell you that it must be more massive than so and so. But there are many different other ways of constructing models of new particles. So I could turn it around, which is if one does a large number of these magnetic dipole moment experiments and electric dipole moment experiments, and with greater and greater sensitivity, they will, and if they continue to see nothing, they do reduce your sort of prior estimate of the probability of there being particles at 5 TeV, 7 TeV, 10 TeV. And which can cause you perhaps to evaluate whether you want to build an accelerator that's aiming for particles at that distance. So in some sense, our negative results are almost more definitive than our positive ones. So it's one nice thing about it is that we're really not in this business. I mean, of course, we'd be very happy to see a non-zero value, but we're not in this business only to see non-zero values.
Okay, so thank you very much, Professor Cornell. So if you join me in thanking him.
Thank you. Thank you. Thank you very much.
So now we invite you to a coffee break just outside and to speak to your colleagues, to our invited speakers, and we'll see you back here at 10:30 sharp, please. Yeah. Thank you very much. That was a lovely talk. con nuestro programa. Ah, llegó Raquel. Ah, sí. Bueno. Pues muchas gracias. Espero que el café haya inspirado muchas conversaciones en cuántica, en estas medidas de alta precisión. Todos quedamos como que wow. Entonces, nuestra siguiente charla va a ser por la profesora Ana María Rey. Entonces, que es muy querida para nosotros, es egresada de la Universidad de los Andes. Ella va a dar su charla en español y pues además no tuvimos oportunidad en el anterior bloque, pero pues le damos muy gratamente la bienvenida a la delegación del Colegio Leonardo da Vinci. Entonces, Ana María, por favor.
Bueno, buenos días. ¿Cómo están todos? Es un gran placer para mí estar hoy con ustedes. Quiero empezar por agradecerles a las organizadoras, Alejandra, Mayerly, Jenny y la universidad en general por organizar este encuentro tan especial. Obviamente también quiero agradecer a nuestros invitados de los Estados Unidos, a Erika, a June y a James que están aquí acompañándonos. Hoy quiero hablarles de relojes. Han oído un poco hablar de relojes antes. Esta es una charla donde espero que todos nos divirtamos y aprendamos. Ok, perfecto, ahora sí, eso, muy bien. Bueno, entonces yo les voy a hablar sobre relojes atómicos y para comenzar esta charla quiero que miren esta figura y que traten de pensar qué es. Pues es una representación de lo que es un reloj atómico que está hecho de átomos y de luz. Estos relojes son los relojes más precisos que ustedes se pueden imaginar. Ahora les voy a explicar por qué y cómo. Pero lo más interesante desde mi punto de vista es que estos relojes no solo se utilizan para medir el tiempo. Y entonces, si ustedes miran con más detalle en esta figura, de pronto ven acá algo, un espía. Con eso yo les quiero decir que con esos relojes espiamos el mundo cuántico. Y por eso son tan interesantes. Nos permiten abrir una ventana para explorar el mundo cuántico. Entonces, en esta charla les voy a contar un poco cómo funcionan los relojes, de qué se tratan, y espero que si no, por lo menos se vuelven ustedes unos relojeros atómicos también, por lo menos sepan lo interesante que es eso y comiencen a investigar más sobre ellos. Ok. Vamos a ver si esto funciona. Voy a comenzar introduciendo qué es un reloj. Bueno, todos sabemos que un reloj es un sistema que mide el tiempo y todos los relojes, todos consisten de dos elementos muy básicos, que es el oscilador, que es lo que hace ticking, y el contador, que es el que cuenta las oscilaciones y con eso nos permite entender o medir el tiempo. Cierto número de oscilaciones nos da una medida del tiempo. Pero paremos un poquito y pensemos por qué nos preocupamos tanto del tiempo. Pues en realidad sabemos que tenemos citas, tenemos que cumplir cierta hora, siempre tenemos que estar temprano, pero pues en realidad la medida del tiempo ha sido algo muy interesante y muy importante desde el principio de la humanidad. Si pensamos desde... No está funcionando mucho. A ver si me hago por acá, a ver. Bueno, si pensamos desde el tiempo de los egipcios, donde hicieron los primeros relojes que medían el tiempo mirando el movimiento de los astros, son relojes solares, y después pasamos a los relojes mecánicos, y obviamente los relojes de péndulo, los relojes mecánicos, y seguimos ahora con los relojes más precisos que nos podemos imaginar, porque el problema de los relojes mecánicos, de los relojes que hacemos a mano, es que todos podemos tener cierto error o hacerlos diferentes acá o en otra parte del tiempo, del planeta. Lo importante acá es que vamos a hacer unos relojes que son universales, que son los mismos acá, en la China, en cualquier parte, y esos son los relojes atómicos que, tal como les decía, son hechos de átomos y luz, y esta es una foto del experimento, de un reloj atómico en un laboratorio. Y yo, a través de mis investigaciones, he tratado de mejorar estos relojes, pero yo en realidad no soy la que hace los relojes. Yo hago la teoría, pero la persona que hace los relojes, que hace el experimento, está acá, es Yunyé, y él es el experimentalista. Pero algo que les quiero contar es que en la física la colaboración entre la teoría y el experimento es muy, muy importante. Así que esto es lo que ha llevado a realizar mejores relojes atómicos, la posibilidad de tener clase de vínculo. Ok, entonces yo les decía al principio de mi charla que los relojes nos permiten espiar el mundo cuántico. Entonces comencemos a entender un poquito qué es el mundo cuántico. Y para eso necesitamos comparar lo que es el mundo clásico con lo que es el mundo cuántico. Comienzo mostrándoles el mundo clásico, que es el mundo del día a día, y con eso aprovecho a mostrarles una foto de Boulder. Aquí es donde vivimos, muy bonito también, como acá, pero muy bonito también. Y es un mundo donde sabemos, es nuestra vida cotidiana, lo entendemos. Utilizamos las leyes de Newton, muchas cosas que es como están metidas en nuestra cabeza. Pero cuando veamos un mundo microscópico, vamos a tener diferentes conceptos. Y para compararlos, quiero introducirles estas dos bolas, una bola azul y una bola roja, y las vamos a poner en esta cajita. Y en el mundo clásico sabemos que es esta bola roja y es esta bola azul, no nos vamos a confundir. Y sabemos que cuando ponemos a rebotar estas bolitas, pues van a rebotar y van a estar ahí por siempre. Bueno, vamos a cambiar ahora estas bolas por átomos o por partículas cuánticas, y lo que va a pasar es que van a comenzar una cantidad de propiedades increíbles. Vamos a tener casos en el mundo cuántico donde tenemos una bola roja, una bola azul, pero también podemos tener las bolas en superposición, es decir, que pueden ser rojas y azules a la vez, y solo sabemos cuando las medimos. Además, cuando ponemos estas bolas a moverse, existe la posibilidad en algún momento que estas bolas no solamente se queden ahí, pero que salgan, que se escapen. Eso se llama el tunelamiento cuántico. Y este tunelamiento cuántico, en realidad, si miramos el premio Nobel de Física este año, fue reconocido a entender mejor este efecto de tunelamiento cuántico en sistemas que después llegaron a construir lo que se llaman superconducting qubits. Perdón, hay veces voy a mezclar inglés y español. Bueno, entonces, ¿por qué los relojes son tan importantes, o por qué el mundo cuántico es tan importante? Bueno, si miramos nuestros computadores, los transistores, que son los elementos fundamentales para la operación de muchos aparatos electrónicos, se construyeron gracias a que entendimos cómo están los metales, cómo están los electrones en los metales, y nos han permitido de verdad no solamente construir computadores muy buenos, pero además, si vamos en nuestro carro y tratamos de mirar dónde estamos, utilizamos un GPS. Y no sé si ustedes saben que cuando operamos un GPS, Lo que pasa es que requiere satélites. Existe un sistema de por lo menos 24 satélites y estos satélites, cada uno de los satélites tiene por lo menos 4 relojes atómicos. Es decir, que los relojes atómicos son fundamentales para nuestro día a día, incluso ahora. Bueno, pero entonces vamos a tratar de entender la diferencia entre un reloj mecánico normal a un reloj atómico. Entonces, el reloj atómico también tiene un oscilador, pero en este caso el oscilador es una fuente de luz, es una onda electromagnética. Esta onda electromagnética puede ser tan rápida que ni siquiera los aparatos electrónicos la pueden medir. Es una onda electromagnética tan rápida que solamente los átomos los pueden medir y estos son los contadores de las ondas electromagnéticas. Así que así es como opera el reloj. Tenemos luz como el oscilador y los átomos que cuentan. Ahora, lo muy importante de la mecánica cuántica es que la mecánica cuántica nos dice que la energía no es continua. La energía en la mecánica cuántica es cuantizada, por eso se llama cuántica, quantus, como las escaleras que no son continuas, sino que son discretas. Entonces eso pasa en los átomos. En los átomos, los electrones no pueden tener cualquier energía, sino que los electrones en los átomos circulan en ciertas órbitas y dependiendo de la órbita que están, el electrón tiene una energía específica. Y lo importante es que para hacer el electrón saltar de una energía a la otra, tiene que absorber luz, pero la luz también es cuantizada. La luz puede ser como una onda, pero también puede ser como un cuanto que se llama el fotón. Entonces Einstein fue los que nos explicó la relación entre la energía y la frecuencia, y porque vamos a utilizar luz de cierta frecuencia que tiene una energía específica para excitar el átomo de una órbita a la otra, de una órbita. Esta constante de proporcionalidad se llama la constante de Planck, pero así es lo que vamos a hacer. Vamos a utilizar el átomo que tiene ciertos niveles de energía y vamos a utilizarlo luz para hacer, cuando la luz tiene cierta frecuencia específica, vamos a hacer que el electrón vaya de una energía a la otra. Entonces, esta diferencia, esa correspondiente entre la energía y la frecuencia, es lo que nos ha permitido definir o utilizar los relojes atómicos para definir el segundo, para hacer una definición inigualable del segundo, porque vamos a medir el segundo asociado con la luz que necesitamos iluminar un átomo para hacerlo pasar de un nivel de energía al otro. Entonces, desde el 1967, la definición del segundo se basa en niveles de energía del átomo de cesio, y lo que vamos a mirar es una transición y vamos a determinar el segundo como aproximadamente 9.000 millones cuando pasan 9.000, bueno, este número de oscilaciones de la radiación que utilizamos para excitar el átomo de cesio de este nivel a este otro, es como definimos el segundo. Y esta es una medida universal que es muy importante, y en realidad utilizamos el cesio porque es un átomo muy simple, es un átomo que está en la primera columna de la tabla periódica. El primer reloj atómico de cesio se hizo en 1955 y era un reloj muy bueno en esa época que perdía un segundo cada 100 años. Pero comenzamos a mejorar los relojes a medida que pasa el tiempo. Es una tabla de los relojes y vemos que la precisión de los relojes comenzó a mejorar hasta que más o menos en los 80 paró de mejorar. Y el problema es que teníamos que hacer algo para lograr continuar la precisión de estos relojes de cesio. Y ese algo lo llamamos enfriamiento láser. Y podemos explicar por qué. Para eso les quiero explicar que el movimiento es terrible para los relojes. Es algo muy malo. ¿Por qué? Ustedes saben, vamos a ver si funciona esta. Creo que no me funciona. Va a tocar que me la pongan. No funciona. Ok, bueno, les va a tocar imaginarse. Este es un tren y es un tren donde van a poner o poder oír las consecuencias del efecto. ¿No? A ver acá, ya. A ver, ¿ustedes qué están oyendo? ¿Ven cierta frecuencia? La frecuencia es diferente con el movimiento. Se lo conoce como el nombre de efecto Doppler. Ese mismo efecto le pasa a los átomos. A todo sufre efecto Doppler. Es decir, cuando el átomo se mueve, vamos a percibir una frecuencia, o el átomo va a percibir otro átomo va a percibir una frecuencia que depende del movimiento. Entonces, si se acerca, va a ser una frecuencia más alta, si se aleja, va a ser una frecuencia más baja. Y eso no es bueno, porque si tenemos nuestros átomos y queremos utilizar la frecuencia para medir el tiempo, entonces el problema es que los relojes se volverían unos relojes muy malos, porque todo dependiendo de la velocidad del átomo se va a medir diferente frecuencia, eso no es bien. Entonces para eso es lo que necesitamos, enfriar los átomos. Estaba dando una charla en México y me recomendaron poner ralentizar, pero creo que aquí no decimos eso, pero enfriar, hacerlos más lentos. Y eso lo hacemos a través de láseres, por ejemplo, por eso los láseres han sido tan importantes y hemos logrado alcanzar temperaturas de microkelvin, donde la velocidad de los átomos puede reducirse muchísimo, a 1 metro por segundo. Entonces, para hacer una comparación, es importante tener un termómetro y saber que los átomos ahorita, en la temperatura ambiente, que es a 300 Kelvin, se están moviendo súper rápido a la velocidad del sonido, es de orden de 300 metros por segundo. Si pensamos en el espacio exterior, que puede ser lo más frío que pensamos, en el espacio exterior está a unos 4 grados, más o menos, Kelvin, de ese orden, pero a esta temperatura es donde el helio se condensa, pero de todas maneras la velocidad de los átomos de helio en esta temperatura son de 90 metros por segundo, súper rápido, no lo podemos controlar. Así que uno de los más importantes labores que hemos podido realizar es la posibilidad de enfriar los átomos para que se muevan muy lentamente. Y eso llevó en 1997 al premio Nobel por enfriamiento láser. Eso fue el Bill Phillips, Quentin Tanuji, Steven Chu, recibieron el premio Nobel por enseñarnos cómo utilizar los láseres para enfriar los átomos. Y para ello lo que hicieron fue utilizar los fotones como las partículas que logran quitarle la energía a los átomos y desacelerarlos y así enfriarlos. Básicamente, quiero decirles que Bill Phillips estuvo acá en el año 2017 y Bill Phillips fue la persona que me conmovió completamente porque él dio una charla en la Universidad de Maryland sobre cómo él enfriaba los átomos. Desde ese momento yo dije, no, eso es lo que yo quiero hacer. Yo quiero aprender cómo enfriamos los átomos y desde ese momento comencé a estudiar física atómica. Una persona increíble. Así que, y él estuvo acá. Lo que él hizo fue que utilizamos los átomos, iluminamos los átomos con láseres, pero interesantemente, lo que pasa es que como los átomos absorben cierta frecuencia, gracias al efecto Doppler, cuando los átomos se están moviendo en contra de la luz, entonces para cierta específica frecuencia logramos que el átomo absorba el fotón. Cuando lo absorba el fotón, recibe una patadita en contra del movimiento enfriándolos. Entonces, así como los enfriamos, vamos a tener, los átomos absorben la luz y reducen su velocidad de esa forma, y lo que vamos a hacer es iluminarlos en todas las direcciones. Eso que se conoce como una trampa una trampa en el vacío donde se iluminan los átomos en todas las direcciones y así logramos reducir la velocidad. Y por eso, eso fue lo que ha llevado a mejores relojes desde esa época. En este caso, hablamos de átomos de rubidio. Una aquí está el video. Quiero tratar de darles un video muy rápido de cómo opera un reloj de cesio. Es un video muy sencillo, pero darle la idea de cómo al enfriar los átomos podemos medir el tiempo. Esto está acá, estos dos personajes muy importantes para nosotros. Uno es Norman Ramsey, que es una de las personas que nos enseñó cómo lograr sincronizar el láser con la transición atómica. Y quiero en particular enfatizar Dan Kleppner, que es un profesor del MIT, y en realidad fue uno de los, está en el árbol genealógico de Eric Cornell y de James Thomson, y desafortunadamente él falleció este año, así que quiero enfatizar lo importante que ha sido la contribución de muchas personas para lograr la operación de estos relojes. Ok, este es el reloj atómico de cesio del NIS. Entonces es una cosa muy sencilla, pero quiero explicarles cómo funcionan los relojes. Entonces aquí están, vamos a atrapar los átomos, en este caso cesio o rubidium, no importa. Entonces este caso es cesio. Entonces lo que hacemos es que vamos a tener los átomos acá, están moviéndose muy rápido. Entonces los enfriamos con el enfriamiento láser, están muy fríos, y ahora con láser los tratamos de darnos un empujoncito y luego los iluminamos con luz de cierta frecuencia. Después esperamos un ratico, los átomos vuelven a bajar y los iluminamos otra vez y miramos a ver cuántos átomos fueron excitados del estado base al estado excitado con cierta frecuencia. Y mire, contamos cierto número de átomos. Luego cambiamos la frecuencia un poquito, otra frecuencia, los iluminamos, dejamos que los átomos adquieran cierta fase, volvemos a iluminarlos acá y miramos contamos cuántos átomos fueron excitados. Y miramos aquí y veremos que más átomos. Y finalmente volvemos a otra frecuencia, más rápida en este caso, los iluminamos, vemos a ver, volvemos a hacer el procedimiento y esperamos a ver este pulso, miramos cuántos excitados y miramos. Entonces, ¿cuál creen que es la frecuencia adecuada? La número 2, porque es donde hay más átomos, los átomos son resonantes y así es como logramos sincronizar el láser a la frecuencia atómica. Ok, seguimos. Vamos a ver.
Él dice que mucha gente malinterpreta este concepto llamado la ley de la atracción. Piensan que se trata de, ya sabes, pensar en lo que deseas.
Perdón, ya. Ahora, el punto es que yo les estaba hablando de los relojes de cesio y los relojes de cesio son los que establecen el estándar del tiempo en este momento, pero los relojes de cesio no son los mejores. Si miran estas dos reglas, esta regla número a la A y la B, y les pregunto cuál regla es más precisa, ¿cuál va a ser? La regla B, porque tiene más tics, obviamente más precisión. Lo mismo pasa para los relojes. El problema es que los relojes de cesio, la onda electromagnética que utilizamos para iluminarnos es muy lenta, porque la transición tiene baja energía. Pero existen otros relojes, que son los relojes ópticos, donde utilizamos una luz mucho más rápida, porque la energía de esta transición es mucho más alta, es 10.000 veces más rápida de la de cesio. Entonces, por eso tienen más tics y tienen más precisión. Esos son los relojes que utilizamos ahora para medir los más precisos. Ok, entonces volvemos a nuestro reloj, que son el oscilador, y vamos a iluminar nuestros átomos, pero el problema es que, a diferencia de la del cesio, cuando vamos a iluminar los átomos, esta transición óptica es tan energética que si iluminamos los átomos, salen volando. Entonces no se puede, tenemos que atraparlos. Y para eso este reloj utiliza, tenemos los átomos, y los átomos los vamos a atrapar también, pero los vamos a atrapar con luz. Entonces, vamos a ver si funciona. Bueno, primero, ¿qué clase de átomos vamos a utilizar para hacer relojes ópticos? No puede ser cualquier clase de átomo, pero en este caso vamos a utilizar átomos que están en la segunda columna de la tabla periódica y en particular nuestro amigo del Gila es el átomo de estroncio. Este es nuestro favorito. ¿Por qué? Porque, bueno, estos átomos de la segunda tabla periódica tienen una transición, que es una transición óptica, que es una transición muy rápida, pero lo importante no solamente es tener la transición óptica, sino que la transición óptica sea de larga vida. Básicamente queremos una transición donde vamos a excitar el átomo del nivel base al nivel excitado y no decaiga súper rápido. En el caso de estroncio, este átomo en el nivel excitado va a durar 100 segundos. Y entre más largo podemos medirlo más rápido y mucho mejor. Prácticamente, muchas veces comparamos los átomos con un péndulo y tratamos de compararlos para qué tan buenos son, pensando en un factor de calidad, que es el radio entre la frecuencia del péndulo y la rata en el que se disipa. Y en este caso, el factor de calidad del átomo de estroncio es mayor que 10 a la 17. Es decir, que es un reloj que cuando lo vamos a poner a hacer ticking, dura sin que pierda nada de energía durante toda la edad del universo. Es un péndulo súper bueno. Ahora, los láseres. No puede ser cualquier láser, porque tenemos que tener un láser súper coherente. Y esto es donde Jun ha hecho maravillas. Ha logrado construir los mejores láseres que se pueden imaginar. Y para imaginarse, dar una idea de qué tan bueno es ese láser, imaginemos que tenemos la coherencia del láser, es como hacer una medida de distancia desde aquí hasta casi la luna, incluso más lejos. Pero este láser tiene un ticking que no es milímetros como lo tenemos ahora, pero el ticking tiene el ticking de la dimensión de una bacteria, 10 a la menos 15, súper chiquito, y durante todo el trayecto de la Tierra a la Luna no pierde ni la información de un solo tic. Así de bueno es ese láser que Jun ha logrado hacer. Bueno, tenemos nuestro láser, que es súper bueno, tenemos el reloj. Ahora vamos a ver cómo los atrapamos, porque yo les dije, no podemos tener los átomos sueltos porque los iluminamos y salen volando. Y para eso utilizamos lo que se llama rejillas ópticas o los llamamos cristales de luz artificiales, que básicamente lo que hacemos es que logramos, no sé por qué no se está viendo tan bien, pero espero que vean, cuando dos ondas interfieren, pueden lograr hacer una onda estacionaria. Eso es lo que hacemos, dos láseres interfieren, forman una onda estacionaria, y esta onda estacionaria es donde la sienten los átomos y sienten como una especie de cajita de potencial que los atrapa. Entonces los átomos quedan atrapados en el fondo de este potencial, y así es como hacemos los relojes, porque están atrapados y cuando reciben la luz, entonces no van a moverse en la dirección en la que se propaga la luz, que es la importante porque es donde pasa el efecto Doppler. No importa mucho que se muevan perpendicular a la luz, pero paralela es importante, así que los atrapamos muy bien. No tenemos efecto Doppler, no tenemos ningún efecto de nada, son muy perfectos estos potenciales. Ahora comenzamos con el dilema. Jun quiso hacer su reloj utilizando átomos neutros porque él sabía que podía interrogar muchos átomos a la vez, porque entre más átomos va a ser mejor señal a ruido. Entonces la idea es, queremos interrogar muchos átomos. Pero el problema es que los átomos no son transparentes, los átomos colisionan, los átomos se ven unos con otros, y el problema es que como los átomos se ven, van a cambiar la frecuencia que medimos cuando hay muchos, y sería terrible, es terrible que la frecuencia que medimos dependa de cuántos átomos hay, eso no es bien. Esas colisiones son muy malas, es nuestro enemigo, el villano que decía Eric, estos son nuestros villanos. Pero Jun sabía mecánica cuántica y sabe que en la mecánica cuántica existe una cosa que se llama estadística cuántica. Para entender la estadística cuántica, primero entendamos que en la naturaleza existen dos clases diferentes de partículas que la vamos a clasificar dependiendo de lo que se llama el spin. Y para el spin es como Eric está hablando de un momento magnético, vamos a pensar los electrones tienen un momento interno momento angular intrínseco magnético que se llama el spin y es un medio, es decir, que puede ser un medio o menos un medio. Pueden circular en una dirección o en la otra, o como una moneda, cara o sello. Y entonces, lo interesante es que tanto los electrones como los protones, todas las partículas tienen spin un medio, pero el átomo está constituido de muchos electrones, de muchos protones, de neutrones, y dependiendo del número de estas partículas, puede tener dos diferentes clases de estadística cuántica. Estos son los bosones, que es en nombre de Chandrasekhar-Bose. Estos son los un poquito aburridos, yo diría, los pobres siempre quieren hacer lo mismo, no son diferentes. Y estos son el caso, por ejemplo, muchos átomos en la tabla periódica son bosones y tienen un número par de protones, electrones, neutrones, porque pues sí, son enteros, un entero. Mientras que los fermiones, que para mí son los más alegres, diferentes, estos son nombrados en honor de Enrique Fermi, y estos tienen spin semientero, es decir, número impar de protones, neutrones y electrones, y estos son todos diferentes. Ninguno quiere hacer nada igual, son los que hacen todos diferentísimos. Y pues, por ejemplo, el helio 3 es un fermión. Entonces, June sabía mecánica cuántica y él sabía que quería utilizar fermiones porque los fermiones van a ser mejores para los relojes, como les voy a explicar. Y en Chile colaboramos mucho. Entonces, no solamente Eric Cornell nos enseñó cómo enfriar los átomos y crear bosones a una temperatura muy baja, lo que se llama el condensado de Bose-Einstein, pero Deborah Jean nos enseñó cómo enfriar los fermiones. Desafortunadamente ya falleció, pero es uno de los ejemplos más impactantes cómo una mujer puede hacer muy buena física. Entonces ella nos enseñó cómo enfriar los fermiones y entonces vamos a tratar de entender cómo las partículas colisionan en la mecánica cuántica. Todo en la mecánica cuántica es cuantizado, incluso las colisiones. Entonces lo que va a pasar es que dependiendo del modelo del momento angular en que los átomos, porque los átomos se mueven y tienen un momento angular, y cuando colisionan, entonces vamos a cuantizar este momento angular. Lo interesante es que los fermiones que son las colisiones más bajas pasan con momento angular L igual a 0, es el más bajo, pero los fermiones idénticos no pueden colisionar con ese momento angular. Por la mecánica estadística prohíbe dos fermiones idénticos tener el mismo estado. Entonces ellos no pueden colisionar. La única forma de que los fermiones idénticos pueden colisionar es cuando le damos energía. Entonces tiene que ser L igual a 1. Pero el momento angular 1 cuesta energía y Jung sabía eso. Entonces dijo, yo quiero hacer mi reloj así porque si enfrío mis átomos y no les doy energía, no van a poder colisionar y vamos a tener un muy buen reloj. Pero resulta que estas colisiones, a pesar de ser suprimidas, no eran completamente suprimidas, y ahí es donde entra la teoría, porque aprendimos, mi rol fue tratar de entender cómo muchos átomos colisionan en el reloj y lograr aplastarlos. Ya no está nuestro villano acá. Y entonces ya tenemos un reloj donde en el 2014 logró alcanzar una precisión de 10 a la menos 18. 10 a la menos 18 corresponde, como es un reloj que no gana ni pierde un segundo en 15.000 millones de años, que es aproximadamente la edad del universo. Así de preciso es ese reloj en el 2014. Pero ahí no nos quedamos atrás. El reloj ha sido mejorando. Y en el 2022, hace ya 3 años, el reloj aumentó la sensibilidad en un factor de 1000 más. Eso es súper importante, porque ese reloj, tanto como Jung nos contó, ha logrado medir qué tan diferente pasa el tiempo dependiendo de la altura, porque Einstein nos dijo relojes a diferente altura van a medir el tiempo diferente, y Jung en relojes de iones antes habían logrado medir esa diferencia en 30 centímetros. En el 2024, Jung logró tener un reloj, medir la diferencia en el ticking del reloj entre dos partes del reloj que están separadas a 1 milímetro, tan solo 1 milímetro, y el experimento logró determinar esta diferencia. Así de preciso es. Ok, ahora quiero darles como una especie de cartoon para que entiendan por qué es tan importante y por qué va a abrir un mundo a entender el mundo cuántico. Para eso, piensen que ustedes son un reloj malo o un reloj normal, y les voy a preguntar qué ven. ¿Qué vieron? Una bolita. Ahora ustedes van a hacer el reloj del Gila y les voy a preguntar, ¿qué ven? Un átomo de hidrógeno. Esa es la idea. La idea es que los relojes atómicos nos van a permitir espiar el mundo cuántico y tratar de entenderlo de la mejor manera. Son como una especie de gafas que nos permiten resolver lo que está pasando a nivel del reloj. Entonces, los relojes atómicos, por ejemplo, en este momento, ya ni siquiera son en una rejilla óptica que es en una dimensión, pero son en rejillas ópticas que son en 3 dimensiones. Y todo, no solamente los estados internos, pero incluso el movimiento de los átomos pasa a nivel cuántico. Entonces, eso es donde nos comienza a permitir explorar el mundo cuántico. El problema es que, tal como les decía, en el mundo cuántico existe la superposición. Entonces, un átomo puede estar en muchos estados a la vez. Muchos átomos pueden estar en muchos estados a la vez. Por ejemplo, imaginemos que tenemos 6 átomos y 6 pozos, y vamos a contar de cuántas formas vamos a poder distribuir estos átomos en los pozos, porque son átomos idénticos. Entonces podemos tener todos los 6 en un pozo, todos los 6 en otro pozo, 2, 2, 2, y contamos cuántas formas, y son 84 formas. Pero si tenemos 60 átomos y 30 pozos, el número de formas posibles es más grande que el mundo de Avogadro. Y un computador clásico, desafortunadamente, no logra almacenar esa información, no lo logra. Así que es cuando necesitamos construir sistemas que operen con propiedades cuánticas de por sí. Entonces aquí es cuando llega Richard Feynman, que también fue un premio Nobel de física en el 82, y nos dijo que lo ideal era tratar de construir sistemas que operaran con propiedades cuánticas de por sí. Así que podemos utilizar esto para entender el mundo cuántico. Entonces él propuso una cosa que se llama simulación cuántica, que es como una forma de emular no todo lo que podemos entender, pero ciertas cosas que son muy importantes. Esto es lo que se llama un simulador análogo, no necesariamente un simulador digital. Vamos al digital más tardecito. Entonces, ¿cómo van a ayudar a los relojes a crear simuladores cuánticos? La idea es que los átomos en los relojes se comportan muy parecido a los electrones en los sólidos. Entonces, los electrones en los sólidos tienen desorden, son difíciles de entender, son muy complicados. Pero los átomos del reloj, como vemos, son muy precisos, muy limpios, son perfectos. Entonces, la idea que tenemos es que vamos a utilizar los átomos en el reloj para emular el comportamiento de estos sistemas más complejos que no entendemos, pero son fundamentales para la tecnología. Por ejemplo, con los átomos en los relojes hemos logrado hacer que los átomos, que son neutros, se comporten como si fueran electrones cargados y sientan campos magnéticos que los llamamos campos magnéticos sintéticos o artificiales. No son reales, pero los podemos hacer comportar. También queremos utilizar los átomos en el reloj, por ejemplo, para tratar de ayudarnos a entender lo que se llama superconductividad a alta temperatura. Entendemos los superconductores, pero no los que pasan a alta temperatura, y si logramos entender eso, podemos crear algo que nos ayude al transporte, a la energía, a muchas cosas. Y también nos pueden ayudar a avanzar la física fundamental, porque hemos predecido que los átomos en el reloj pueden comportarse con las simetrías que exhiben los quarks y los sistemas de altas energías. Los protones están formados por quarks y los quarks tienen una simetría que se llama SU3. No les explico qué es SU3, pero lo interesante es que los átomos en el reloj tienen simetría hasta SU10, es decir, que podemos expandir las posibilidades de entender esta clase del comportamiento a altas energías. Finalmente, también Feynman nos dijo, no solamente podemos hacer un computador análogo, pero lo más interesante sería un computador digital, donde todas las partículas que forman el computador están hechos de elementos cuánticos. Entonces, si vamos a ver en un computador clásico, los que están tomando computación ven que están operando en bits, que son ceros o unos, en un sistema binario. En el sistema cuántico, lo que vamos a tener es quantum bits, qubits. Entonces, los bits pueden estar estado 0, 1, pero 0, 1 o solo 0, 1. En cambio, en el qubit pueden tener una superposición de 0 y 1 a la vez. Pueden estar en estos dos estados a la vez. ¿Y por qué es importante? Porque, bueno, si tenemos dos bits, podemos tener 4 estados, 0, 0, 0, 1, 1, 0, 1, 1, tal como le dice, existe la superposición y puede estar en todos esos estados a la vez. Si tenemos 3 bits, podemos estar 8 estados, 10 bits, 1024, 30 bits, muchos más, 500 bits, muchísimos más. Pero lo importante es que en sistemas cuánticos existe lo que se llama el paralelismo cuántico, que un computador cuántico, porque puede almacenar todos esos estados a la vez, puede hacer estas operaciones en paralelo. Entonces, en vez de hacer una a la vez, si tenemos, por ejemplo, 3 qubits, podemos tener almacenados todos estados a la vez y hacer operaciones simultáneas, que eso sería súper interesante. Y además por ser tan rápido, puede lograr romper todos los códigos de criptografía, una cantidad de cosas fantásticas. Está en su infancia, sin embargo, está hasta ahora comenzando, pero estamos muy emocionados de que logre funcionar. Entonces, ustedes van a ver en internet que tienen IBM, Google, todas esas empresas están tratando de hacer computadores cuánticos que se llaman superconducting qubits, pero nosotros también tratamos de hacer computadores cuánticos con átomos y con iones. Y que existe, el futuro es súper interesante. Y lo importante es que solamente es el comienzo. Entonces aquí yo quiero decirles, bueno, los computadores cuánticos, el reloj no va a ser un computador cuántico, pero pues nos puede ayudar a entender cuáles son los requerimientos de coherencia que necesitamos construir para hacer un computador cuántico pronto. Ahora, la nueva generación de relojes puede ser incluso mejor de lo que les dije. Es increíble ahora, pero puede ser muchísimo mejor. Y para eso vamos a utilizar lo que se llama enredamiento cuántico, porque resulta es que como los átomos son indistinguibles, son ruidosos, desafortunadamente, porque la mecánica cuántica es ruidosa. Pero enredándolos podemos volverlos menos ruidosos y crear incluso mejores relojes. Y además, tal como les dije, el reloj atómico ha logrado medir la diferencia en el tiempo tan solo en 1 milímetro. Pero ¿qué pasa si lo hacemos incluso más pequeño? Podemos comenzar a entender la conexión entre la física cuántica y la gravedad, que todavía no se entiende, que puede ser algo súper importante. Y realmente es solamente el comienzo. Hay una vista brillante por delante y ustedes son los encargados de construir y al hacernos entender y hacerla mejorar. Así que con eso les agradezco mucho. y termino con una foto de las personas que han hecho posible todos esos. Son muchos más, no caben en esta fotografía, pero pues es un trabajo que se hace a través de sus estudiantes, postdocs y obviamente colaboración. Pero así que los invito a tener el sueño de estudiar mecánica cuántica, construir relojes y ser los que van a llevar a posible estas mejoras. Muchas gracias.
Muchas gracias, profesora Ana María Rey. Tenemos tiempo para 2 o 3 preguntas, entonces levanten la mano para que les llegue el micrófono. Aquí hay una pregunta.
Buenas tardes, bueno, buenos días. Quisiera decir que cómo han manejado el principio de incertidumbre de Heisenberg en cuanto a estos relojes atómicos. Considero que es un problema muy grande y quería saber si lo han solucionado, cuáles han sido los problemas.
Perfecto, muy buena pregunta. Primero, el principio de incertidumbre pasa desde el punto de vista de la energía y el tiempo, ¿sí? Entonces, entre más preciso sabemos, hay un delta de energía, una incertidumbre en la energía con incertidumbre en el tiempo. Entonces, por eso es que necesitamos relojes que tengan coherencia muy, muy larga para reducir la incertidumbre de energía. Por eso necesitamos tener un reloj de estroncio o algo así, donde el reloj va a tener una coherencia muy, muy, muy larga para reducir la incertidumbre de la energía. Ahora Yuna está haciendo unos 2 relojes que son utilizados, un reloj nuclear, donde el tiempo de vida es incluso mucho más largo y la incertidumbre en energía va a ser más pequeña. Esa es una forma. Pero también, cuando vamos a medir el reloj, la frecuencia del reloj, vamos a medir, tenemos 2 niveles de energía y vamos a medir si el átomo está en un nivel o en otro nivel, pero también vamos a medir una superposición. Y en la superposición hay cierta incertidumbre, ¿verdad? Y por eso estoy diciendo que aquí, no sé si sabes, el angular momentum, hay una incertidumbre entre Sx, Sy, Sz, y esa incertidumbre es exactamente porque los relojes son ruidosos. Esto es lo que nos lleva a los ruidosos. Entonces, tratando de reducir la incertidumbre en una cuadratura, nos permite medir la otra, tener menos ruido en la otra cuadratura. Y eso es lo que queremos hacer en un futuro. Todavía hay comienzo, pero todavía no son los mejores, pero esa es la idea.
Listo, gracias. Y mi segunda pregunta sería, si un reloj atómico es expuesto a una velocidad cercana a la luz, ¿aún podría funcionar o todavía se está como discutiendo ese pequeño?
No, pues lo que pasa es que vamos a tener el principio de energía masa, es decir, E es igual a mc cuadrado, y la verdad, por ejemplo, pues obviamente no va a ser posible, pero lo que te digo es que cuando Jun mide que el reloj tiene un ticking diferente cuando lo tienes acá o cuando lo subes 1 milímetro, eso está relacionado con la relación mc cuadrado, porque el átomo en el estado base tiene diferente masa al átomo en el estado excitado, y la diferencia de masa corresponde porque existe una diferencia de energía que traduce la masa del estado excitado multiplicada por c cuadrado es igual a la masa del estado base c cuadrado más h barra omega, que es la energía interna. Así que lo que quiero decir es que no necesitamos movernos a la velocidad de la luz para todavía comenzar a ver esa física.
Listo, muchas gracias.
¿Cómo se espera que la diferencia de altura que estaban midiendo con los relojes de mayor precisión sugiera alguna conexión entre la relatividad y la cuántica? O sea, ¿se supone que la diferencia de altura va a sugerir la existencia de un gravitón?
Todavía no creo, pero la interesante, por ejemplo, es mirar qué pasa cuando logramos medir diferencias que llegan a ser a una distancia de la longitud de onda, por ejemplo, de la luz que estamos utilizando. Incluso vamos a mirar qué pasamos cuando llegamos a una distancia que sea el tamaño del átomo. Entonces, todas las propiedades cuánticas van a estar súper importantes. Entonces, vamos a mirar si existe algo que no corresponde, porque en este momento no sabemos cuál es la conexión entre la gravedad y la cuántica. Entonces, si vamos a sistemas microscópicos más pequeños, podemos chequear si algo que pensamos que era completamente necesario en la cuántica no funciona, o al revés, si tratamos de mirar algo que pensamos que funciona como entonces sabemos que el potencial es MGH, y si vemos alguna corrección de eso sería muy importante. O podemos mirar a ver, no sé si existe un enredamiento que se daña debido a la gravedad.
Hola, muchas gracias por la charla. Hay una pregunta que me surge en la parte experimental, es que uno usualmente, o bueno, lo que yo conozco, nunca me había cruzado con algo tan novedoso, es pues como patrones de fotonización que uno tiene en el átomo, por decir. Expones el átomo a una cierta frecuencia y él emite sus electrones. Aquí no entiendo por qué.
Lo que pasa es que no le damos tanta energía para que se salga. Le damos la energía para que pase de un nivel a otro, pero también le puedes dar una energía súper grande para que el electrón se salga y deje de estar atrapado. Es decir, existe el átomo se forma por las fuerzas electromagnéticas, ¿verdad? Y si a un momento le das tanta energía que el electrón deja de estar bound, ¿cuál es la traducción de bound? Ligado al núcleo, va a lograr salirse y eso se pasa. Nosotros lo que pasa es que le damos mucha menor energía, pero la ionización puede pasar.
Ok, pero entonces la pregunta es, en vista que no se ioniza o casi no se ioniza, ¿cómo miden el paso del tiempo?
Yo traté de explicar un poquito con ese video del reloj de cesio. Simplemente lo iluminamos y miramos cuánta cambió la población del estado base al estado excitado. ¿Se acuerdan que lo que hacemos es que los experimentos pueden medir si el átomo está en el estado base o si el átomo está en el estado excitado? Eso se puede medir porque dependiendo, solamente cuando está en el estado excitado, lo puedes darle cierta energía para que el electrón, para que la luz, se llama fluorescencia, donde vas a iluminar el átomo del nivel, y cuando está en el nivel excitado puede absorber luz, cuando él está en el estado base no. Entonces puedes contar cuántos fotones son emitidos por muchos átomos. Tenemos muchos átomos y podemos medir cuántos átomos están en el nivel excitado, cuántos átomos estamos en el estado base, y como la luz que está en resonancia es la que transfiere más del estado base al estado excitado, entonces así podemos sincronizar la luz con el átomo.
Ok, y en ese orden de ideas, por ejemplo, conozco investigaciones donde se omite esa parte y únicamente se estudia el patrón de fotonización que bota en el espectro. Pero en este caso, como tengo la presencia de un contador, ¿eso me repercute en alguna incertidumbre de mi medida?
Pues sí, nosotros no hacemos eso. Si quieres ionizar el átomo es otra cosa, pero hay gente que utiliza, mucha gente, por ejemplo, ioniza los electrones, y cuando el electrón vuelve al átomo, entonces suelta un pulso de luz, y eso es un pulso de luz súper corto que utilizan para hacer láseres muy cortos que se llaman ¿cómo se dice?
Atosegundos.
Atoseconds, sí. Entonces, existen ciertos experimentos donde sí quieren específicamente ionizar el electrón y utilizar la propiedad de que cuando vuelve emite cierta luz y que es súper corta, pero nosotros no utilizamos eso. Pues la incertidumbre, tal como lo mencionaba, está en cuando medimos, lo que al final queremos medir es una fase, y medir una fase no necesariamente en mecánica cuántica podemos medir, la fase pasa en una cuadratura como en un plano XY, entonces si medimos la fase a lo largo del X, no sabemos la fase a lo largo de Y. Más o menos esa es la idea. La posición y el momento en la mecánica cuántica no los podemos medir con precisión perfecta.
Vale, muchas gracias.
Voy a estar acá, así que pueden preguntar después.
Bueno, pues buenos días, muchas gracias por tu charla. Mi pregunta va más a que, bueno, últimamente pues he estado leyendo sobre estados comprimidos de luz y pues vi que la aplicación, o sea, pues está en esto, en relojes cuánticos, en relojes atómicos. Y ahora mi pregunta es, pues serían dos, ¿no? O sea, primero, ¿qué es o sea, para ti, ¿qué es cuadratura? Ya que es un concepto como muy ambiguo.
¿Cuadratura?
Sí, o sea, primero sería como...
En el caso de los átomos que estamos haciendo, lo que puedes pensar es que los dos estados del átomo se pueden imaginar como una flechita, ¿verdad? Y si el átomo está en el estado excitado, la flechita apunta arriba. Si el átomo en el estado base, la flechita apunta abajo. Si el estado no está en una superposición, la flechita apunta en la mitad. Pero cuando apunta en la mitad, puede moverse, es decir, esta es la dirección de tu flecha, y existe un plano perpendicular, ¿verdad? Entonces puede moverse, como es perpendicular, es un sistema dos-dimensional, y entonces puede tener una cuadratura a lo largo del eje X o a lo largo del eje Y. Es decir, puedes pensar como si fuera un vector, más o menos. El spin es como un vector, y no, si sabemos la dirección a lo largo de Z, no vamos a saber qué es a lo largo de Y y X, y estas son las cuadraturas. Y cuando logramos tener más conocimiento de lo que pasa en la dirección de X, no sabemos en la dirección Y, así más o menos. Pero lo que te invito es que el profesor Thompson es el experto en entender cómo modificamos el ruido cuántico, y él va a dar una public lecture mañana.
Dale, muchas gracias. Y bueno, pues respecto a ese mismo tema, normalmente cuando uno pues ve en cursos introductorios o por decía, los estados de los comprimidos, ellos hacen esa relación con el principio de incertidumbre de Heisenberg, ¿no? Entonces ellos llaman a uno la amplitud y a la otra la fase.
Sí.
Y ellos lo que hacen es, bueno, yo utilizo el operador de rotación o de squeezing, y lo que hago es rotar en el plano, o sea, ese vector, ¿no?
Sí.
Y generar ese vacío electromagnético. ¿A qué hace referencia esa operación en la que yo giro ese paso?
En este caso son rotaciones. Lo que pasa es que, cuando tienes el sistema de dos niveles, y cuando tienes un campo magnético, entonces lo que pasa es que el spin va a comenzar a precesar, pues realmente como un giróscopo con una flechita, y lo que va a precesar es que va a comenzar a moverse del plano X al plano Y. Eso es exactamente eso, la cuadratura X, y comienza a precesar y va a la Y, y así. No, creo que no me estoy explicando muy bien, pero podría explicarte con más detalle.
Dale, muchas gracias.
Bueno, primero, gracias por tu charla. Y mi pregunta va que justamente ahorita en octubre un equipo del MIT publicó un paper donde hablan de usar la información guardada en la fase global del átomo para disminuir el ruido. Entonces lo que hicieron fue medir la fase global del átomo luego de que lo golpeó la luz, y vieron que la fase global guarda información sobre la frecuencia de esa luz. Entonces, ya que dijiste que están intentando implementar técnicas de reducción de ruido en el reloj de June, bueno, en su reloj.
El reloj del MIT todavía no es un reloj atómico. Ellos han tratado de lograr esto en los estados hiperfinos, pero no en los estados ópticos. En el reloj de June sí han logrado hacer lo mismo en los estados ópticos, y June tiene un paper de hace un mes donde ha logrado reducir el ruido en algo que es realmente útil para la transición. En el MIT van a hacerlo después seguro, pero por ahora no lo han hecho.
Pero entonces ese proceso que usó June para reducir el ruido es similar a este proceso de fase global, ¿es el mismo?
Se llaman non-demolition measurements, ¿cómo se llaman? Mediciones de no destructivas. Yo te puedo explicar, ahorita no te puedo explicar en detalle, pero vas a la charla del profesor James Thompson, él te va a explicar cómo se hace todo, él es el pionero de hacer eso. Así que vaya a la charla de él, porque yo tengo 1 minuto y él va a tener toda 1 hora para explicar eso.
Gracias.
Bien, muchas gracias. Entonces, so we now move to our panel discussion that's going to be moderated by Professor Alejandra Valencia. And so we invite to the panel to Professor Ana Maria Ray, Professor James Thompson, Professor Yun Yi, and Professor Eric Cornell.
Claro.
Buenos días todavía. Mi nombre es Alejandra Valencia, soy profesora del Departamento de Física. Gracias por estar aquí con nosotros celebrando el Año Internacional de la Ciencia y Tecnología Cuántica. So what we want to do now in this last session in the morning is to have a little informal conversation with our wonderful guest here today to discuss just a little bit of what you have been listening in the morning. So I have to open my notebook. Look, I did my homework, but I always need to have it with me. So because I am really very happy to be here with the 4 of them. So with Professor Eric Cornell, so Nobel laureate for getting the coldest temperatures that we know. And now we have heard about all these interesting experiments, like also this idea of doing with these precise measurements experiments of high energy physics, at least for me, is very interesting. I'm going to jump here. Professor Yun Yi, that we have been hearing also today, these wonderful experiments with high precision, the most wonderful clocks. And also Professor James Thompson, that does this wonderful control of quantum systems to get also high precision and to be the king of the noise control. So as Ana Maria said, and tomorrow we can listen more details about this. In particular, I am very happy to, not to introduce, you already know Ana Maria, but to be here sitting close to Ana Maria, because actually she is an alumni, I don't know if it's working, is it working? She is an alumni from here, from Uniandes, and from a more personal point of view, we have been together, let's say in some way, since we were in kindergarten. I think that since we were 4 years old, we did together, like kindergarten, primary school, secondary school. She was always getting the best grades in the class. And then actually we did together here them undergraduate studies. So we shared the classroom for a lot of time actually. And then we also were very close when we were doing our PhD studies, because we were both in Maryland at different universities, but close by. So, and then each one of us continued then in different direction, and physics anyway has always bring us together. So from a personal point of view, it's very nice to be here. So, okay, so let's to start this conversation. I want to ask you, exactly like I was saying, you all come from close but different corners from science. So I would like you to tell us, please, like in a couple of sentences, for example, in the case of Professor Eric Cornell or Ana Maria, a couple of sentences to summarize like the research that you do. And then the same thing then for Professor James Thompson and Professor Junji. But yeah, like a couple of sentences to summarize what we have been listening this morning. So,
Okay, so buenos dias. I've been working for many years with lasers, atoms, molecules, first to make things as cold as I possibly can, and then beyond that to measure things as precisely as I possibly can. I think all of my research falls into those two categories over the years.
Right, I'm a theorist, so I don't do experiments, I do theory. And what I love to do and have done for many years is try to model and understand how matter and light interact and how we can control these systems to make them useful for metrology, for understanding the quantum world, and hopefully in the future for better technologies.
Let's see. So in my lab, we laser cool atoms, we trap them, we levitate them, and we keep them in the quantum world so we can play games in quantum mechanics. But what we really like to do is get the atoms to interact with each other. And we like to have interactions to improve our ability to measure the universe around us. And we also like to create these interactions for the idea of quantum simulation that Anna Maria introduced earlier. To sort of have a quantum system that emulates physics that you would see in other quantum systems.
I'm Jun Yi. I'm from the same institute as my good friends and colleagues. And you can probably not get, by this time, you get a sense of we are all control freaks. Essentially, when Eric and James says we are going to cool atoms down, what they're trying to say is they're just capture each atom and put them in a certain quantum state that they know what the atoms are actually doing, so that you can perform measurements on them to give us time. And in my career, I went from lots of atoms completely uncontrolled to finally get into a single atom, captured in the middle of a pair of mirrors, to go back into many atoms to be now in quantum state controller state. And as Anna Maria's talk really beautifully reflected on, is this gives us a tool to measure time very precisely.
Very much. And okay, Ana Maria, like you already told us in your presentation that you fell in love with cold atoms, listening one of Professor Bill Phillips' presentations. But then can you track, like if we go before, like your high school maybe, or undergraduate studies, the moment in which you say that you like it, physics, and then I don't know if quantum physics or if quantum physics was more in the graduate studies.
Right. Yes, when we went together to high school, La Nakano, it was a very small high school, and our teacher professor was Victor Caro, and for me, writing an equation that can predict the motion of a ball was fantastic. So I asked him to give me more books and more books because I needed to solve more problems. So then, well, of course, I knew I wanted to do physics. At that time, we only knew classical physics. We didn't have too much modern physics, or very little, very little. But really, what changed my mind here are two key people. Professor Bernardo Gomez. When I took Introduction to Quantum Mechanics, oh my God, that's so beautiful. I mean, I really needed to do quantum mechanics. I had no doubt. And the other person that changed completely my view of physics and the beauty of physics was the Professor Aldona Gabriunas. She taught us thermodynamics, statistical mechanics. So this is the only class that I failed one exam. So this is, well, I mean, she taught me so much. And well, then after I took this class with her, then I had to decide what to do during my thesis. And then el Professor Rafael Bautista, I think I see him there. I mean, it was an amazing inspiration. I have already told them that he told me general relativity, but that's the most important advice that I got from him is he said, look, I will teach you general relativity. It's okay, you can learn, it's very exciting. But promise me that when you finish and go to grad school, you do something apply, something that really connects with the experiment. And well, that's what I did, and that has been the best part of my career.
Okay, thank you, Anna.
I'm going to chime in there, actually.
Yeah,
you know, all of these names that Anna Maria is talking about, you might imagine that she's talking about them just here because she's at the university. She talks about you in Boulder as well. She really means it. You had a big impact on her life based on the fact that those same names are mentioned in Colorado all the time.
Good, very nice. So, Professor Cornell, so now, going back to your Bose-Einstein condensates work. So, Nobel Prize, very important, very excited. Then you were telling us this morning and yesterday about these experiments with the electron. So how was the, let's say, kind of transition, maybe is the word, to go from one of these topics, the BEC, to measure properties of the electron? Also very excited experiments. Do you want also another Nobel Prize with these experiments? And how was the transition is actually the first. But,
leaving aside the Nobel Prize, the transition was for me very gradual. You know, I've been working in Bose-Einstein condensation, very cold atoms for a long time. And the first thought I had is, well, the slower things move, that means they're very cold. If they're very cold, they move slowly, and the slower they move, the more carefully you can measure them. I thought, well, my lab, I have the coldest things in the world. They move the slowest in the world. I should be able to make the most precise measurements. What would be a really useful measurement, interesting measurement to do with something that moves so slowly? And then as now, one of the sort of outstanding questions in precision metrology is the dipole moment that I talked about earlier today. And so I thought, oh, well, I will very naturally put together the Bose-Einstein condensation. They go together very well, and I'll use it to make a precise measurement of the electric dipole moment. And then I spent 3 or 4 years as on the weekends and the night times when I wasn't working on my regular work, thinking, how can I put these two things together? And I did not come up with a solution. But I spent all this time thinking about how I could use cold atoms to measure this electric dipole moment, and then I decided what I really want to do is measure the electric dipole moment. I don't have to use cold atoms to do that. And so I started very, very gradually, at first with just 1 or 2 students working on a smaller project. And then gradually I got to the point where I thought this is too complicated for me, and Jun was willing to contribute 2 of his students to the project also, which made an enormous difference. And gradually, like a boulder rolling down the hill and gathering momentum, it became more and more of my work, to the point where I was no longer able to concentrate on the ultra cold atoms anymore. And so I sort of closed those projects also gradually.
Professor Jun, so as we have heard, so you have the best clocks ever. So can you also tell us about to summarize, because in some sense we have been listening during the presentations, but the implications for fundamental science applications of these very precise clocks?
Yeah, it's funny that Eric was saying I got a BECs around the turn of the century, right? People have been thinking about how do I apply BEC to different kinds of physics. And I was a young fellow that was just hired into Jella. And we had another fellow called Deborah Jing. Anna Maria mentioned her name. She's another giant, really. Unfortunately, she's no longer with us on this earth. But she's another giant, happened to be Eric's postdoc. She conquered the world of fermions that Anna Maria very eloquently explained. So as a young researcher, I was thinking to myself, yeah, exactly the same thought. Except that I wasn't thinking about EDM, I was thinking about clocks. How do I use this coldest atoms that we have as a resource to build the clocks? And along the way, there's tremendous amount of technology you have to develop. How the atoms are interacting with each other. It turns out can be very positive thing, can also be a very negative thing, depending on the scientific goal. But now we have systems where by learning more and more about how you can control their interactions, putting more and more atoms in there, even including getting their noise to be entangled. So at this point, you can turn this back into a scientific tool. If you can continue to push the frontier of measuring time, another factor of 10, another factor of 100 better, we'll be starting to see how gravity start to influence the dynamic evolution of a quantum mechanical system. So one is a theory of a very macroscopic scale, one's a theory of a very microscopic scale, and it's so lovely to see them coming together and influence each other. So we very much hope, just like EDM, another few decades later, probably was discover new physics. We would like to get into a new regime of that people really haven't seen before, how gravity start to influence the time in a way that not only influence the GP, how we transmit time for technological applications, but really have fundamental new insights of quantum mechanical systems under curved space-time.
And Professor Thompson, so with this capacity of controlling noise and arriving to this high precision, can you please tell us, like in a way that we can grasp easily, what is this high precision that we are talking about? Like if we can put it in some scales that maybe for us when we hear 10 to the minus 18, so maybe the age of the universe, but so if you can help us to grasp better this.
Sure. So in my lab, we don't always do precision measurements, but we develop new tools for precision measurement. We really like to ask, what does the universe allow us to do, and what does it not allow us to do? How can we take the things we know about and combine them in creative, interesting ways to make better measurements around us? That's one of the things we do. And so one of the things that is talked about, and I will talk about this in my public lecture, is that in some sense, single atoms, they're pretty noisy. Like a single atom has a lot of quantum noise built into it. And if you can do better by using lots of atoms and having them sort of averaging down the noise associated with these many atoms, but what if you could get them to sort of cooperate with each other so that if one atom's noise kind of fluctuates up, another atom's noise will fluctuate down. In order to do that, we create something called entanglement. So we're going beyond single particle physics. In other words, we're not just running many copies of the same experiment in parallel in order to get many, additional precision. Now we're really taking advantage of the fact that we have many atoms, and we know about this concept called entanglement, where you build a kind of very fundamental quantum correlation between the atoms, such that one atom knows about the quantum state of the other atom, and they can conspire to be quieter. So if you want to think about it, it's kind of like saying you have a clock hand, and that clock hand could really be measuring time, but it could also be measuring accelerations or rotations or a magnetic field or an electric field. It's a very generic concept, but there's some quantum fuzziness in sort of where that pointer is pointing. And by entangling these atoms with each other, we're able to sort of get them to conspire and make a sort of more pointy hand so you can actually measure these things out. That's an example of the kinds of things we do. We also do lots of fun experiments, but that's an example of what we do in our lab.
Is quantum fuzziness. So Ana Maria, maybe to summarize again, just it will stay in our minds. So yes, you work theoretically, differently from these other three professors that are experimentalists, in light matter interaction. So can you give us some fundamental physics implications that come from this deep understanding that you have been getting also, and also from an applicative point of view?
I love many body physics, so I am interested in modeling not only one particle. I mean, one particle is still fascinating, but I want to understand how many particles change their behavior and can give rise to emergent properties that we could not understand just by considering a few particles. That's the challenge, because in the quantum world, when you start to study many particles, then you start to not being able to have the memory in a computer to actually model, because we are used to put all this information in the computer and the computer speed up an answer. But we are reaching the point, I mean, many years back, that we cannot model even 100 particles. The Hilbert space, or the number of states that you need to put in a computer, breaks down. So what I love to do is trying to understand what part of the Hilbert space, or what are the simplified behaviors that I have to keep in my computer to be able to predict what we want to see. For example, in the clock, I cannot model 10 to the 4, 10 to the 3 atoms. I cannot. But I can understand what is the simple model that I need to derive in order to determine when the collisions are going to be bad for the clock. And I think that's one example of how I can tame my atoms, or what are the conditions that I have to have in an experiment, so these collisions are not going to modify the properties. Or in the context of quantum simulation, for example, how can I make an atom behave like a superconductor? And we have done that. I mean, we don't have superconductors, we don't have charged particles, but anyway, we can simulate their behavior in our lab.
Okay, thank you. So as I mentioned, Ana Maria is a theoretician, and she actually also was telling us about that in the presentation, and works close to experimentalists. So Professor Thompson, I want to ask you, how is this a collaboration to work the theory and the experiment, like, yeah, this collaboration, and actually in your everyday basis, do you meet every day and look the Hamiltonians that Ana Maria has? Or
It's fantastic. So, you know, one of the things that in particular is a lot of fun at GILA is that we really like the idea of collaborating with each other. And, you know, there are people who help to nucleate those interactions. One of them is Ana Maria. She's very good at interacting with and proactively interacting with experimentalists. So, you know, I would say that when we're both in town, we have weekly joint group meetings between experiment and theory. And what's great about that is that, you know, Ana Maria will write down a Hamiltonian on the board. If you're young and you haven't gotten to Hamiltonians, it's just a way of describing quantum mechanics. And for her, sort of, you know, understanding the system flows from the Hamiltonian, you know, forward. And as I've told her, you know, Ana Maria, I've looked like really hard in my lab, and I've never spotted a Hamiltonian anywhere in my lab. So what I know is that I've got this little laser that's pushing on my atom here, and then I can sort of construct the clockwork of interactions. Another way of phrasing it is I tend to think of things in terms of unitaries. Yeah. Unitaries that are generated by the Hamiltonians. If you want to phrase that in a mathy way, that's kind of how I think about it. And what I would say is it's incredibly productive to have two different pictures sort of interacting with each other and sort of enriching each other. And it has sort of spurred creativity, you know, creative ideas for us in our experimental group. Conversely, you know, creative ideas of theory proposals the other way. Ana Maria was talking about these, we have now published papers where we do emulations of BCS superconductors and dynamical phases. Yeah, I mean, come on, that came from Ana Maria. Yeah. Like, we had the right tools to do it, and she just helps us to identify how to make these intellectual connections. So I can't say enough about the idea. More theorists and more experimentalists should be getting together and talking to each other. It's a really fruitful thing.
Yeah, I would like to add in this context, once, like in January, we were in a conference, and we met Professor James, Professor Ana Maria, and myself, and as the people from my group knows, I am all the time saying, please tell me, what is noise? How do I measure noise? What is that? So I am like this old woman that, hey, what is noise? I don't understand. What is this? So I say, look, I am with Professor Thompson, with Professor Ray. I am going to understand what is noise. So I went first, to Ana Maria. I was shy to ask Professor Thompson. So, Ana Maria, this noise, I don't understand. And Ana Maria said to me, But James was there on the table. Alejandra, go and read the theoretical book in quantum optics. And I said, that doesn't help me. And also I have read this book 10,000 times and I still don't know what is noise. So, and then James was there, and the point is what is noise? What I have in my lab is a spectrum analyzer, a cable, I move a knob. How do I recognize all this noise that then, like the title of your paper, Ana Maria or the theoreticians come with these concepts? So it's very nice to do this merging, but it's also a very big exercise of like a language issue. So no, I don't know, for me.
We definitely sort of use different languages and we push back and forth. And if you showed up, you might think we're not so buddy-buddy with each other. Oh, we are. We just want to solve the problem. Like that, we just want to solve the physics. Yep.
Yeah. So no, thanks for sharing that. Okay, so for you all, so you come from you are visiting us from Colorado, from this like institute where is merging the university and also the National Institute of Standards and Technology. So this merging of GILA and NIST. So really like an academic perspective and a very like applicative, important for the economy of the country as is a metrology institute. So can you comment on this kind of merging, what is good, is bad, some of your thoughts about this merging or a synergy between this public government and this part of the academic studies? I don't know, Professor Jun, do you want to start telling us?
Sure. Yesterday we were taking on a city tour, thanks to you. And we went to see the square where the Parliament and Supreme Court and Congress, it's just a very impressive place. And we were told just behind the building of a Congress, there is an observatory. And that used to be the place to set time for Columbia. And this is actually an example. Back in the US, observatory is called a NIST, National Institute of Standards and Technology, has a very long-term mission, which is to set standards for commerce. Well, time is certainly one of them. If you want to do trades and so on, you better know when you put your stamp on your records and so on. So it has a very long-term sort of a mission for economic development, for the well-being of the nation and for the world. On the other hand, GILA was created as a joint institute with the university to go forward, to do as creative as you want, to do open-ended research, but with some implication that maybe one day when we want to build better standards, we can count on you. You got all these creativities, you have been training all these students. Maybe you'll develop better standards for NIST in the end. And I find that like loose-end management, they are not really breathing on your neck at all. There's some very long-term mission. Please just go, do as much fun work as you wanted, because that's where the creativity will be shining. But don't forget, there is one mission, which is to create better standards in the end. And I find that to be very powerful. And really, over the course of 60 years of GILA, lots of technology came out of GILA because of we want to do fun science with it, and we'll build our tools if there's nothing available out there. And so I find that partnership very powerful.
So maybe like following a little bit these ideas, like now, how do you see or you imagine the role of a university in these new times, in the sense of how do we put basic research versus more technical training, or how do we have a balance? Do we need a balance? I don't know. Can you, Professor Cornell, comment a little bit on that, please?
Sure. I actually think that, technology advances very rapidly. And so if we try to say, well, we're not going to do research, what we're going to do is just provide certain specific technical trainings. The problem with that is that it takes 4 years to go through university, maybe another year to get a master's, something like this. And at the end of that time, the very particular skill you have learned may not be that useful anymore. It may not be where technology is going and what have you. So I don't think that there's a real tension between providing, as a university, providing good technical training and pursuing the research, because I think the one can lead so very clearly to the other. If we're doing research, it means we are trying to solve problems that we don't know the answer to. And these are the most interesting and the most difficult problems. And yes, they come up in universities, but they come up in factories, they come up in development, industrial development centers. If they knew how to solve the problem, it wouldn't be a problem. So I think that as our students do research, it's a little bit like going to a gymnasium, except instead of lifting heavy weights, they're solving hard problems. And this, I think, hard problems for which they don't know the answer. And that develops the kind of confidence, call it muscles from lifting heavy weight, but it's brain muscles, the kind of confidence that allows them to go out into the world, encounter technical problems for which they have not received specific technical training because there is no technical training, because it's a new problem, and yet contribute. So I think that the students who have come through these oftentimes challenges of solving basic problems, technical problems in basic research, oftentimes go off and become extremely successful in the industrial world. Within Jill, I think we're all very proud of the fact that the vast majority of our students are participating in high-tech industry. In many cases, they become national leaders, entrepreneurs, founders, CEOs, chief technical officers, and where they learn that kind of expertise was not explicitly getting technical training, although they really were.
Interesting. Okay, and to finish this conversation, so we are celebrating the 100 years of the development of quantum mechanics. So if we take a historical perspective, can each of you tell us, please, like one story or fact or moment in this historical development that you find particularly interesting, that it calls your attention, that it seems cool to you? So I don't know, Professor Thompson.
So for me, the part of quantum mechanics that I find most interesting is that it's this ad hoc thing that had to happen, which is that the quantum measurement process had to be introduced, and the idea of wave function collapse. And I think that we've refined our understanding of wave function collapse over time to extend to the concept of, well, it's associated with entanglement. But I just think, in some sense, when you write down the Schrodinger equation, which is this sort of mathematical differential equation that describes non-relativistic quantum mechanics, that, well, it's a differential equation, it's a wave equation. But for me, where the rubber meets the road, in other words, where you really know you're doing quantum mechanics is when you say, I start measuring things. And the measurement has a back action on the system. How do we describe that back action? The measurement process has noise associated with it. And to me, I just find that really fascinating. To me, that just feels like the heart of quantum mechanics.
Ana Maria.
For me, quantum statistics perhaps is amazing, fascinating. I mean, understanding quantum statistics let us understand how metal behaves, semiconductors. I mean, for experiments like what we do at GILA, quantum statistics is fundamental for determining how different systems are going to behave as they enter the quantum world. Yes, because in classical world, we don't have that idea. But is this different between bosonic particles, fermionic particles, that has led to me to revolutionary developments? And there are many things that I still do not understand. And for me, the idea of trying to better use quantum statistics for generating entanglement. Something that is pending. I think it's something that is missing even in quantum computers now. And so I think there is still many new things that we need to understand and learn.
Professor John.
Oh, okay. For me, I just feel that quantum mechanics makes me very humbled because I don't understand very much. You know, when I was a graduate student learning about quantum mechanics, well, you learned things can tunnel behind the wall. That makes you wonder what the heck the particle can actually go through the wall. And it turns out, if you think from the wave function point of view, you will say, oh, light can penetrate through dense materials, so maybe that's not so strange. But then you just ask yourself, what is actually the wave, the quantum mechanical wave? Oh, somebody will tell you it's a probability distribution function and so on. Is this something really associated physically with the particle? No, it's a really mathematical description of the information. It just, to me, this is a very deep, and in fact, what's fascinating is, fast forward 30 years, this year is the 100th birthday of quantum mechanics. There was a survey, Nature actually did a survey to a bunch of physicists. And we went to this little island called Helgoland, where Heisenberg came up with this idea of matrix. And they did a survey, said, do you believe in wave? No, what in your mind, what is a wave? Is this a mathematical creation? Is it a real physical property? And so on. They was like giving 5 choices. And it turns out, among all these physicists, there was very diverse opinion. And so this tells you how much, and this is actually what intrigues me. Things are still mysterious, and entanglement, as mentioned by my colleagues here, very mysterious. How could you have 2 particles very far apart and yet maintain correlation much better than any classical means can ever possibly achieve? What is that? So it's the mystery part of quantum mechanics makes me very intrigued. And for most of our daily life, I think I forgot who said this. You just shut up and calculate. You know, in the sense of don't try to understand the philosophical meaning of quantum mechanics. Just calculate. Calculation turns out to be very precise, and you can do experiments with the quantum mechanics every day. You feel good about it, but sometimes you occasionally do dream about the meaning of this.
Professor Cornell.
So James here and I are sort of scientific brothers in the sense that we had the same PhD advisor. And our scientific great-grandfather was a guy named Norman Ramsey, also a Nobel laureate. And in the 1950s, right now, quantum mechanics is 100 years old. But when quantum mechanics was a youngster in the 1950s, only 30 years old, I think you asked us, like, what was a moment that really popped out for you? And this was a historical moment that I still find very amazing in some sense. Norman Ramsey was trying to understand how to use light. In his case, it was radio waves and not light, but it's the same thing, as we know, to measure frequencies very precisely. And he was troubled by the fact that when you shine the light at something, as we know, you are measuring it, you're disturbing it, you're perturbing it. It's nice to be able to not do that for a little while. And he came up with this amazing idea where you hit something with a little pulse of light, or radios, or microwave as you prefer, and then you stop shining light at it. And the thing just sits there, but it has built into it now, you have written upon it a quantum phase, and it remembers that phase. It can remember that phase for a long time, and then you ask it about the phase again sometime later. But in between, when you impose the phase and ask the phase, it sits there undisturbed with the phase evolving without a reference to anything like your microwave synthesizer or anything like that. This way of measuring frequencies, sometimes called Ramsey's method of separated oscillatory fields, I learned about this as an undergraduate. I was probably 20 years old. And to be fair, even when I was 20 years old, quantum mechanics was much younger than it is now. But it was, I think, one of the very first, since we're talking about not just science, but quantum technologies, It was one of the very first practical applications of quantum technology. Basically, we use this idea of coherence, which seems like a very abstract idea, to make a better measurement. And so I very much identify as a great-grandchild of Norman Ramsey, and this is one of the things I most admire about him.
Nice, very interesting. So thank you very much. So I think with these questions, we finish this conversation, but not before opening for some questions from the audience. Or comments, doesn't need to be questions or comments. Do you need a microphone? Yeah, we have a lot of microphones. Yeah.
Hello. Thank you very much for the panel. And I have a question regarding, so through Monday and Tuesday, you have all of you have talked about like the joy of the work, because I know this is hard work, of course. But do you have a specific moment when you think like when you feel like a lot of joy, maybe when you solve a hard problem, maybe in an experiment, or for Maria's case, in like you have a great idea to solve a problem, like you feel like so much joy when you finally solve it after so many times, so much work, something like that. Maybe for it can be for all of you. I don't know.
I will tell you maybe an example of that, which sort of made me fall really, really in love with physics, and sort of said, yeah, I'm going to do this. As an undergrad, I was doing research, and we were measuring atomic transitions for testing QED. The details don't really matter. But it was at this accelerator. It was a particle accelerator. And I was left alone in the lab to run that experiment overnight. And the data's coming in, and in real time, I'm analyzing the data. And I know it sounds trivial, but I was like, in the whole history of the world, I'm the only one who knows this transition frequency in nitrogen, helium-like nitrogen. And it was like, you know, explorers used to get on boats, and they would go across unknown oceans and feel like, even if it wasn't true, but they would step on some piece of land, they'd be like, no one's ever been here before, I am here. And I think a lot of physics, you have those moments where you're like, you know what, no one's ever done this before, and we just did it. And I find that very satisfying, and that was my first experience. And so in some ways, I think this idea of being explorers, that's hard to do now. But I think in science and in physics, as an example of that, you can do it. And I take a lot of joy in that.
Thank you. Any other comment?
I'd like to take a jump from where James is, because sometimes my students will say, well, we're working very hard, and yet look, all around there are groups which are far ahead of us. You know, I spent all this time working, and in the end, all I managed to understand, I came up with this measurement, and I happened to look in a journal which was published 20 years ago, and someone has already published that before. And what I tell them is, you know, you can embrace the romance of discovery, even if you're discovering it for yourself. You know, the actual sensation of figuring out something, that little, I mean, just to use a sort of anatomical idea, the release of endorphins in your head, you know, that suddenly makes you think, ah, yes, like that's real. And just because you're not the first person to do it doesn't make it any less real. And so, if you like to think of it this way, it's practice for a time when you might be the first time to do it. But I actually don't think of it that way. I think it's valid in its own sense. And so occasionally I'll think of something and I'll work it out, and I'll say, look at the implications of this. Okay, I'll give you an exact example. I was probably in, I don't know, 7th grade or something like that. And we were learning about the square numbers, you know, 4, 9, 16, 25, 49. And you know, I noticed that as you go from 1 to 4, that's a step of 3. But if you go from 4 to 9, that's a step of 5. And 9 to 16 is a step of 7. And as you go from one square number to another, you keep adding a bigger and bigger odd number to it. You know, the next odd number to it to go. And I thought, wow, that is, look at that. I figured this out all by myself. And I think even as a 7th grader, I may have suspected that I was not the first human being among the, probably there had already been 10 billion human beings to walk the earth. One of them probably figured this out. I felt good about it. So whatever it is that you discover, like, that's real, that's you.
There was another question.
So, hello, thank you for the panel again. And my question is maybe more for Alejandra and
Alejandra, but why for Alejandra?
and Ana Maria.
Okay, good. So, but I cannot see who is talking.
It's here.
Okay.
So, I am a master's student. I'm very young in science, but in the small time I've been in science, I've seen this surge of interest in science, especially in Latin America and Colombia, that makes me very happy. And my question is, in these times that there's so much interest, what do you think is the role that Latin America and Colombia has in this, well, in science in general, because science is a very collaborative, it's an effort of the whole world, I think. And what is the piece that Latin America and Colombia, in your perspective, plays in this revolution, especially as there's more interest in this in the public?
Okay, so I would say, like, for example, here, in Colombia. So I am always very proud to talk about the physics that we do in the physics department here at Uniandes. So I think that we are able to train our students to have a discussion about physics with Professor Cornell, Professor Ana Maria, James Thompson, June, from GILA. That is like an institute that we cannot compare in terms of economical founding between Uniandes or GILANIST. But I am proud of the fact that our students can go and discuss the physics. Okay, they have the lasers that for sure, I don't know, cost a lot of money, and we don't have that laser, although they also have a history of investment that it doesn't started 2 years ago with a huge amount of money going, a delta function, from 0 to 10,000 million pesos. So it's something that has a historical development. So, but then you are asking to the role of Latin America. So I think that we are training people to talk this language, to understand. That will be good for us as a country, because if we think about, for example, these quantum technologies, the people that knows says that, I don't know, like in 10 years, various of the technologies that are going to appear in our life are going to have these quantum ingredients. Some of them already have it. And even though if we are not the producers of that technology, we are going to buy it. And I always think that is good, that the people that is going to buy it knows what they are talking about. Maybe not all the Hamiltonian of everything, but to have some ideas. So I find it also as a responsibility to educate our community that then anyway is integrated in the planet, I don't know. And then just maybe in some sense I am a little romantic. The people that knows me knows that I think that we do science here in Colombia. Also, we are very privileged to be sitting here discussing about the most precise clocks in the world, like in an environment as Colombia. We are really very privileged. And as human beings, just in my opinion, no, what makes us to be humans, this curiosity, this going not just to cross the Atlantic to discover new land, but to go to this frequency line of thorium. So I also find it like, as being a human, happy human and good human. So I don't know if I replied, but I talk a lot.
Yeah, I think I'm very proud that Colombian people, we are very charismatic and we are very smart. We are. I mean, But the important part is that we know we have to learn how to challenge, how to guide our thinking, the energy in good things. So we have to educate people. That's our task for the future, trying to educate people and trying to guide their intelligence to do great things. And I think at the moment we don't do that as well as we should. I mean, we have to start since kindergarten. I mean, and our job, our task is to make this future generation of young people to learn science, to learn not only science, but to build their thinking to do great things. And this is our most important contribution now for Colombia, for Latin America, for the world. I also don't know if I answered your question, but that's how I feel.
Definitely, thank you. Well, hello, I am a student from first semester, so I was wondering if there was any moment in your life when you said like, I can't continue doing it. It's beyond me doing it.
So everything associated with math, everything associated with science was just easy peasy for me. And then I hit, it was my sophomore year, I hit a mathematical methods for physicists course. And it was a moment where I was sitting and we were dealing with special functions. And I thought, why don't I understand this? It was a moment where it was the first time I went, what the heck? And I thought, wait a minute, does this just mean I'm not cut out for it? Like maybe, you know, like maybe I've just been fooling myself all this time. And like now I've realized this is just not, maybe I'm not good enough, you know? And I think that everyone hits a moment where you realize, look, it's just gonna take hard work. You're gonna have to work hard. And if you work hard at it, you can figure it out. But you're just gonna have to devote yourself to saying, yeah, maybe this isn't easy for me, but that's okay. I can just work really hard and I will figure it out. And for me, that was a big growing experience at the time. So that was a moment where I sort of thought, do I belong in this field or not? And it turned out, yeah, just keep working hard.
Well, when I joined Harvard, I can tell you that I cried so many days. I joined Harvard and I wanted to work with one professor, and then I was writing mails. Can we talk? No response. Can I talk? No response. Then I talked to another professor and he told me, well, yes, unfortunately, this guy thought that you should not be here. And it was frustrating. I mean, I couldn't believe it because I wanted to work with this person and I couldn't believe it. So, but sometimes we have to believe that we can do it. So at that time I said, okay, I can cry all day or I can work super hard, as James said, and show this professor that I do deserve it. And that's what I did. I mean, it was hard, super hard, but at the end we became friends and it worked out. So sometimes, and I think especially women, we're very susceptible to people say you cannot do it. And I think our job is to tell ourselves, actually we can. And well, and work hard because that's no choice. If you want to make something work, you have to work super hard. And well, hard, and I mean, of course you have to have a little bit of luck, but you can do it. That has to be here inside you.
So I don't know if Alejandro, you want to say a closing remark?
Okay, so no, thank you all for being here, the public for listening, participating, our panelists, our colleagues, friends, for this wonderful conversation, for sharing your thoughts, and no, so let's have lunch. So
yes,
thank you very much.
For the afternoon, so at 2:30, we'll have another public talk from Professor Cornell, so from 2:30 to 3:30. And after that, we'll have a poster session. So the students will show us their research. So you're all invited to that. And through the activities that we will have on Thursday, so the technical session by Professor Thompson, technical session by Professor Ana Maria Ray, and then on Friday we'll have the public talk by Professor Thompson, a coffee with Professor Thompson where you can ask questions in a more relaxed way. And in the afternoon on Friday, we'll have a conversation of women in STEM, which is for all of us here, Mayerlin, Ana Maria, Alejandra, and myself, very important. So you're all invited to come to that. And then after that, we'll have a coffee with Ana Maria. So see you back at 2:30.
Yes. And just a big applause to organizers of the event, because otherwise it would not.